On November 3rd, 2025, someone pulled a database entry that shouldn't have been remarkable. Just another orbital solution from NASA's Jet Propulsion Laboratory, the kind of mathematical housekeeping that happens thousands of times a year as telescopes track objects through our solar system. But buried in that file was a number that made no sense. A30. Perfect. Pristine. 0. For 20 days, an interstellar visitor called 3I Atlas had been accelerating through our solar system, changing its velocity in ways that required constant thrust. And yet, according to the most precise astrometric data humanity can gather, it had not deviated from its orbital plane by a single measurable amount. Not a wobble, not a drift, not even a tremor perpendicular to its path. Natural comets don't do this. They can't. When ice sublimates from a tumbling nucleus, when jets blast gas into space from asymmetric vents, when solar pressure pushes unevenly on an irregular surface, physics demands motion in 3 dimensions. The universe doesn't do 2-dimensional thrust from natural objects that aren't designed. But here's what should make you sit up in the darkness if 3I Atlas is accelerating through some kind of outgassing the way comets are supposed to behave. Then it just lost roughly 10% of its total mass during its passage near the sun. That's billions of tons of gas and dust expanding outward at hundreds of meters per second, forming a cloud that should be visible to every major telescope on Earth. On December 19th, 2025, when 3I Atlas makes its closest approach to our planet, we're going to point those telescopes at it and look for that cloud. Either it's there massive and undeniable, confirming that we're looking at the strangest comet ever discovered, or it's not there, and we have to explain how an object accelerates without ejecting the mass required to cause that acceleration. That's not how physics works. That's not how anything works, unless the rules we thought we understood are incomplete. Tonight we're going to examine something that arrived from beyond our solar system, carrying chemistry that shouldn't exist, moving with precision that defies randomness, and displaying properties that have Harvard professors using words like artificial in peer-reviewed papers, and NASA remaining conspicuously uncomfortably silent. This isn't about believing in aliens or conspiracy theories. This is about data, cold, hard, reproducible measurements from multiple independent observatories, all pointing towards something that doesn't fit our models. And when reality doesn't match the theory, it's not reality that needs to change. We're 45 days from answers. 45 days from December 19th, when the Hubble Space Telescope, the James Webb Space Telescope, and hundreds of other instruments will turn toward a small dark object coasting through the night and measure whether the debris cloud exists, whether physics behaves as expected, whether we're looking at a comet or something else entirely. So settle in, get comfortable, because we're about to explore 10 impossible anomalies, 3 competing hypotheses, and 1 profound question. What if the third interstellar visitor to our solar system is trying to tell us something about the universe we don't want to hear? The data is there, the clock is ticking, and the cosmos, as always, waits patiently for us to catch up. The ancient Greeks believed comets were atmospheric phenomena, not visitors from space, but disturbances in the air above our heads, omens and portents that signaled the deaths of kings. They were wrong about the location, but perhaps right about the significance. Some visitors do change everything. On a night in early 2025, automated telescopes scanning the southern sky detected a faint smudge of light moving against the background stars. The discovery itself was unremarkable. Hundreds of asteroids and comets are spotted every month by our robotic sentinels. But within days, something extraordinary became clear. The trajectory was wrong. Not wrong as in miscalculated, but wrong as in this object isn't from here. When astronomers plot an orbit, they're solving a puzzle that Isaac Newton first cracked in the 17th century. Every object bound to our sun travels along an ellipse, a stretched circle with the sun at one focus. The shape of that ellipse tells you everything: how far the object ventures, how fast it moves, whether it's an asteroid from the inner system or a comet from the frozen reaches beyond Neptune. But some orbits aren't ellipses at all. Some are hyperbolas, open curves that come from infinity and return to infinity, swooping past the sun once and never coming back. These are the interstellar visitors objects that don't belong to our solar family, but are just passing through on journeys that began in other stellar systems perhaps billions of years ago. 3IO Atlas. The designation means third interstellar object discovered by the Atlas Survey, joined a very exclusive club. Before 2017, we had never confirmed an interstellar visitor. Then came Oumuamua, a small elongated object that tumbled through in 2017 and vanished before we could study it properly. 2 years later, Borisov appeared, a proper comet actively outgassing, giving us months to examine its chemistry and confirm it was indeed a visitor from another star system. Now, 6 years after that first detection, we have our third confirmed interstellar object, and it's nothing like the first two. Let's start with size. Oumuamua was perhaps 100 meters across, about the length of a football field. Borisov was larger, maybe 400 meters, comparable to a small mountain. Early observations of 3I Atlas suggested something between 5 and 46 kilometers in diameter, depending on how reflective its surface might be. Even at the conservative estimate, we're talking about an object 1,000 times more massive than Borisov, 1,000,000 times more massive than Oumuamua. Think about that progression for a moment. The first interstellar object we detected was tiny. The second was small. The third is enormous. If you were sampling randomly from a population where small objects vastly outnumber large ones, which is how nature works with asteroids, with comets, with any debris population, you would expect to find many small objects before you found a large one. Instead, we found a giant in our third detection. This is rather like reaching into a jar of mixed beans, mostly small lentils, with a few rare kidney beans, and pulling out 3 beans in a row that get progressively larger. Possible? Yes. Lucky extraordinarily, but size is only the first anomaly. Let's talk about trajectory. When 3I Atlas entered our solar system, it was moving at about 60 kilometers per second, relative to the Sun, faster than either of its predecessors. Speed makes detection harder because the object spends less time in the inner solar system, where our telescopes are concentrated. Finding a fast-moving object suggests they might be more common than we thought, or we got very lucky, or there's something about this particular object that made it easier to spot despite its speed. The trajectory itself is retrograde, meaning 3I Atlas is moving opposite to the direction the planets orbit. About half of comets from the Oort cloud, our solar system's distant reservoir of icy bodies, arrive on retrograde paths, so this alone isn't unusual. What is unusual is the inclination, or rather the lack of it. The ecliptic plane is the flat disk where Earth and the other planets orbit. Most Oort cloud comets come from random directions above the plane below it at steep angles, because the Oort cloud is a spherical shell surrounding our solar system. There's no preferred direction. An interstellar object having formed in some other star system and been ejected into the galaxy should also arrive from a random direction. The sky is a sphere. All directions should be equally probable. 3I Atlas arrived moving within 5 degrees of the ecliptic plane. It's traveling in the disk of the solar system just backward. The probability of this happening by chance is about 0.2%. Not impossible, 1 in 500 odds, but certainly getting our attention. And then there's the timing. The object reached perihelion, its closest approach to the Sun, on October 29, 2025. Perihelion occurred at 1.36 astronomical units from our star, a bit farther than Earth's orbit, closer than Mars. But from Earth's perspective, the Sun was directly between us and 3I Atlas, solar conjunction. For roughly 2 weeks, from mid-October through early November, the object was hidden in the solar glare, unobservable by ground-based telescopes.
This happens. Geometry is geometry, and sometimes objects pass behind the sun from our viewpoint.
But consider what else the trajectory accomplished. In early October, 30-year Atlas passed within 30 million kilometers of Mars, close enough for spacecraft orbiting the red planet to observe it. In early November, it passed Venus at 97 million kilometers. In March 2026, it will pass Jupiter, 3 major planets all encountered within months of each other. If you wanted to design a trajectory for an interstellar probe to observe the major worlds of our solar system, you would choose something very much like this, a retrograde orbit in the ecliptic plane that brings you past Mars, Venus, and Jupiter in quick succession. And if you wanted to perform some operation or maneuver unobserved by the most technologically advanced planet in the system, you would time your closest approach to the sun for when Earth cannot see you. Is this proof of intent? No, nature doesn't care about our observation schedules. The object's trajectory was set millions or billions of years ago when it was ejected from whatever system spawned it. The timing of perihelion during solar conjunction from Earth is simply chance 1 in 4 odds, roughly depending on how you calculate the observability windows. But coincidences accumulate, and we're just getting started. By the time 3I Atlas reached perihelion, astronomers had already noticed something strange in its spectrum, the rainbow fingerprint of light that reveals chemical composition. The object was glowing in lines characteristic of nickel. Lots of nickel, accompanied by carbon dioxide, carbon monoxide, cyanide, and various other volatiles you'd expect from a comet. But the nickel abundance was wrong, and the iron that should accompany nickel, the element that always appears alongside nickel in cosmic abundance ratios, was absent, not faint. Absent. This was unprecedented. In every meteorite ever analyzed, in every asteroid, in every sample of primitive solar system, material nickel and iron occur together in roughly constant proportions because they were made together in stellar furnaces and condensed together in protoplanetary disks. You don't get one without the other unless something very specific has separated them. And then there was the mystery of the water, or rather, the lack of it. Comets are supposed to be dirty snowballs, ice mixed with dust and rock. When they approach the sun, the ice sublimates, releasing water vapor that forms the characteristic coma and tail. Water should dominate the outgassing, but spectroscopic observations from the James Webb Space Telescope revealed that 3I Atlas was releasing carbon dioxide as its primary volatile, 87% by mass, with water making up only 4%. This is backward. This is a comet that formed in conditions so cold that carbon dioxide ice somehow dominated over water ice, suggesting birth in the outermost darkest reaches of a protoplanetary disk, far beyond where we typically expect comets to form. A massive object, a fast trajectory, perfect ecliptic alignment, encounter timing with multiple planets. Chemistry that violates expectation. And we haven't even gotten to the acceleration anomaly yet. In our solar system, we have millions of years of experience watching comets. We know how they move. We know that sunlight and outgassing create forces that nudge them off purely gravitational paths. NASA's JPL Horizon system, the computational engine that predicts where objects will be months or years in advance, accounts for these non-gravitational accelerations with mathematical parameters.
3 numbers: A1 for radial acceleration toward or away from the sun, A2 for transverse acceleration along the orbit, and A3 for out-of-plane acceleration perpendicular to the orbital plane. On November 3rd, someone pulled the latest Horizon solution for Atlas. The numbers staring back from the screen were A1, 1.66, X10, AU day 2, A2, 7.09, X10, 7, AU day 2, and A3, 0. 0. Perfect, pristine, impossible 0. An object had been accelerating for 20 days through our solar system, and it had not wobbled out of its orbital plane by any measurable amount. That's the anomaly that leaked. That's the number that shouldn't exist. And that's where our mystery really begins. There's a particular quality to silence in science, not the absence of sound, but the absence of explanation. When data arrives that doesn't fit the models, there's usually a rush to understand it. Papers, proposed hypotheses, tested conferences convened.
But sometimes when the data is sufficiently strange, there's simply quiet, as if speaking the numbers aloud might make them too real. The JPL Horizon system is NASA's computational crown jewel for solar system dynamics. It's not some fringe algorithm run on a graduate student's laptop. This is the system that plans spacecraft trajectories, that predicts eclipses decades in advance, that told us where to point our telescopes to catch New Horizons' flyby of Pluto and Arrokoth. When Horizon gives you numbers, those numbers are backed by millions of observations, rigorous mathematical frameworks perfected over decades, and the collective expertise of the planetary science community. So when Horizon says an object is accelerating, it's accelerating. Let's understand what those parameters mean. When a comet approaches the sun, ice on its surface heats up and sublimates transitions directly from solid to gas without becoming liquid. This outgassing creates jets of vapor and dust blasting off the surface. If those jets are asymmetric, which they always are because comets are irregular lumps with rotation and varying surface composition, they create thrust. The comet becomes, in effect, a natural spacecraft with poorly controlled thrusters that fire chaotically as different regions rotate into sunlight. This thrust manifests as non-gravitational acceleration. The A1 parameter captures push toward or away from the sun, usually away as sunlit jets blow material outward. The A2 parameter captures push along the orbital direction, either speeding up or slowing down the comet. And A3 captures push perpendicular to the orbital plane, causing the comet to drift north or south of its gravitational path. For any natural comet with asymmetric outgassing, all three parameters should be non-zero. Take Halley's Comet, which we've studied for centuries.
Its non-gravitational parameters are well-documented radial transverse and out-of-plane components, all present, all varying as the comet's rotation carries different active regions into sunlight. The three-dimensional dance of forces creates a complex but predictable deviation from purely gravitational motion. 3I Atlas has a 3 referable to 0. For 20 days of sustained acceleration, it has moved in 2 dimensions, only along its orbital plane with no vertical deviation whatsoever. The implications are profound. If outgassing is causing the acceleration, then the jets must be arranged with perfect geometric precision to cancel out any perpendicular component while maintaining radial and transverse thrust. The nucleus would need to have active regions positioned so that any upward push is exactly balanced by a downward push, any northward thrust paired with a southward thrust, while net forces in the plane accumulate.
This is rather like balancing a spinning plate while riding a unicycle while juggling, except the plate is a several kilometer-wide chunk of ancient ice tumbling through space. The unicycle is an elliptical orbit subject to solar gravity and radiation pressure, and you're juggling gas jets that turn on and off as sunlight plays across an irregular surface. Nature doesn't do precision engineering. Nature does chaos constrained by physical law, and the results are messy. But let's be fair. Let's consider whether there's a natural explanation. Perhaps the nucleus isn't tumbling. Perhaps 3I Atlas is in a special rotational state, what planetary scientists call a dead rotation, where the object spins around a principal axis with the same face always pointed roughly sunward. If the active regions happen to be arranged symmetrically around that face, you might get in-plane thrust without perpendicular deviation. Possible, yes, in the way that it's possible to flip a coin 100 times and get 100 heads. The physics doesn't forbid it, but probability makes it unlikely. And there's another problem: the amount of acceleration observed is enormous. When the Atacama Large Millimeter Array ALMA, one of the most sensitive radio telescope networks on Earth, tracked 3I Atlas during perihelion, they found it was 4 arcseconds off its predicted position. 4 arcseconds doesn't sound like much. It's the angle subtended by a basketball viewed from 40 kilometers away. But at the distance 3I Atlas was from Earth, 4 arcseconds translates to thousands of kilometers of deviation. Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard and former chair of the university's astronomy department, did a calculation that's now circulating in the academic community. If the acceleration is caused purely by outgassing gas jetting off the surface carrying momentum, then conservation of momentum tells you exactly how much mass must be ejected to produce the observed thrust. The answer is staggering, somewhere between 10 and 15% of the object's total mass. If 3I Atlas has a mass of 33 billion tons, the lower bound estimate based on its size and density assumptions, then it lost between 3 and 5 billion tons of material during its passage near the Sun. 3 billion tons of gas and dust ejected into space, carrying momentum away from the nucleus. That gas doesn't vanish. It expands outward at the thermal velocity of sublimated volatiles, a few hundred meters per second for carbon dioxide and water. By December 19th, 2 months after perihelion, that expelled material will have formed a diffuse cloud extending millions of kilometers from the nucleus. The cloud will be faint, yes, spread over an enormous volume illuminated by distant sunlight, but it will scatter light and it will emit spectral lines from molecules like carbon dioxide and carbon monoxide. It should be visible. More than visible, it should be obvious to any telescope that looks carefully. December 19th is our test. That's when 3I Atlas makes its closest approach to Earth at 267 million kilometers. That's when Hubble Webb and hundreds of other instruments will turn their attention to this object and measure everything they can measure. If the debris cloud is there massive and unmistakable, then the mystery has a natural solution. The acceleration was caused by outgassing. The in-plane confinement, while unusual, is just a statistical fluke combined with peculiar rotation. 3I Atlas is a comet, a very strange comet with exotic chemistry, but fundamentally a comet. If the cloud isn't there, or if it's orders of magnitude smaller than required, then we have a problem. Because you can't accelerate without ejecting reaction mass unless something else is pushing you. Internal propulsion. Directed energy, something we don't have a natural explanation for. And that's not even the strangest part of the data. There's another observation, more recent, more controversial, harder to confirm, but impossible to ignore. During late October, as 3I Atlas approached perihelion, multiple solar observatories were monitoring the region near the Sun. These instrument satellites like Stereo and GOES-19, designed to study solar activity and space weather, caught glimpses of the comet in their fields of view. The images are difficult to interpret because solar observatories aren't optimized for faint comets. The sun's overwhelming brightness saturates sensors, and pulling out a dim comet requires heavy image processing and background subtraction. But in those processed images, some analysts reported seeing something unexpected. The comet appeared to brighten extremely rapidly as it approached perihelion, with a brightness scaling roughly as 1/distance to the 7th power. Normal comets brighten as they approach the Sun, but typically as 1/distance squared or cubed. To the 7th power is an extraordinarily steep dependence, suggesting either massive sublimation or some other energetic process ramping up dramatically near the Sun. And more controversially, there were reports, tentative, preliminary, unconfirmed, that the color of the object looked unusual. Comets are typically reddish, reflecting sunlight filtered through dust that scatters away blue wavelengths. But some analysts thought 3I Atlas appeared closer to solar color, or even slightly blue-shifted. If real, this would require explanation. Blue light from a dust-enshrouded comet is difficult to produce naturally. You'd need either massive ionization of the gas creating blue emission lines, or you'd need a thermal source hotter than the sun's surface producing shorter wavelength radiation. Or you'd need the observations to be wrong artifacts of image, processing, calibration errors, misinterpretation of saturated data from instruments never designed for this kind of measurement. We won't know until December, when proper telescopes with proper calibration can measure the spectrum carefully. But the possibility hangs in the air like smoke. What if 3i Atlas isn't just reflecting sunlight? What if something inside it is glowing? There's an old principle in medicine: when you hear hoofbeats, think horses, not zebras. The common explanation is usually correct. When you see a patient with a cough and fever, you diagnose flu or pneumonia, not some rare tropical disease. But sometimes the hoofbeats belong to zebras, and sometimes, very rarely, they belong to something that's not a horse at all. Right now, we're listening to hoofbeats from beyond our solar system. They sound wrong, they sound controlled, and the more carefully we listen, the stranger they become. November 3rd, 2025. Two things happened on the same day. Someone pulled the JPL Horizon solution showing that impossible A3 does occur 0, and someone posted a confession to an anonymous image board. 4chan's X board dedicated to paranormal topics, UFOs, conspiracy theories. The digital equivalent of late-night radio shows about Bigfoot and government cover-ups is not where serious scientific discourse typically occurs. It's where anyone can post anything with complete anonymity, where signal and noise are indistinguishable, where truth and fiction blur until even the posters themselves might not remember which is which. So when an account appeared, claiming to be a PhD researcher working with the European Space Agency, with ongoing access to combined observational data for 3i Atlas, the immediate and correct response is skepticism. This could be anyone. A bored graduate student, a science fiction writer, a troll crafting an elaborate hoax. The internet is full of anonymous claims that dissolve under scrutiny like cotton candy in rain. But here's what makes this different: the technical details are accurate. The post opens with a confession. For months, I have been part of a formal working group that has tried and failed to reconcile this object's behavior with any known class of natural celestial body. The official position is that 3i Atlas is a uniquely active but otherwise natural comet. This position is no longer tenable. Strong words, career-ending words, if true, and if the poster's identity were ever revealed.
Working groups like this are typically composed of senior scientists, postdocs, and specialists from multiple institutions, all bound by professional norms that discourage public speculation before peer review. Breaking ranks to post on 4chan would be professional suicide, unless the data is so disturbing that someone felt compelled to speak. Consequences be damned. The post then lays out 5 core problems, each explained with enough technical sophistication to suggest the author knows what they're talking about. First, the outgassing paradox. The object is venting about 150 kilograms of gas and dust every second. This is observed, measured, confirmed by multiple telescopes, including the James Webb Space Telescope and ground-based observatories. The mass loss rate is not in dispute, but when you apply conservation of momentum, one of the fundamental laws of physics, as inviolable as the speed of light or the conservation of energy, the object should recoil. It should move in response to the momentum carried away by that expelled gas. The post uses a vivid metaphor. It's like watching a howitzer fire a shell with absolutely zero recoil or smoke or bang. It is a constant, violent event with no consequences. If you eject 150 kilograms every second at typical outgassing velocities of a few hundred meters per second, that's tens of thousands of newtons of thrust. For an object with the mass of 3i Atlas, that thrust should cause measurable acceleration. The JPL data confirms the acceleration exists, but the acceleration pattern doesn't match asymmetric outgassing. It matches something pushing from inside, or something with impossibly perfect symmetry.
The author describes their working group checking the data 100 times with all available instruments. The outgassing is real. The lack of expected consequences is real. The only way the physics works, they claim, is if the object has the mass of a small moon crammed into a space no more than 2 to 3 kilometers across. This brings us to the second problem: density. To not recoil from ejecting 150 kilograms per second, the object would need to be so massive that the momentum change is negligible. The Post suggests a minimum mass of 33 billion tons in a 3-kilometer sphere. That's a density approaching that of iron or nickel, far higher than any comet or asteroid. It's the density of a planetary core, not an icy body. But if 3I Atlas is that dense, we encounter a third problem: statistical impossibility. Our surveys of interstellar space have only just begun. The Vera Rubin Observatory went operational earlier in 2025. Before that, we'd confirmed exactly 2 interstellar objects: Oumuamua in 2017, Borisov in 2019. Both were small. Oumuamua, maybe 100 meters across, Borisov, around 400 meters.
Now we have 3I Atlas, potentially 5 to 46 kilometers in diameter, 1,000 to 1,000,000 times more massive than its predecessors. And we found it within months of turning on our new survey capability. If objects this massive are common enough that we detected one almost immediately, the Post argues, then the galaxy is not just dotted with debris, it is swarming with them. Our models of what gets ejected from solar systems would be wrong by factors of 10,000. Either we got impossibly lucky or these objects aren't debris at all. Fourth, the chemistry. Here the Post gets specific: pure atomic nickel steaming off the surface, happening at temperatures where it should be frozen solid. This is not gradual sublimation like ice turning to vapor. It is a switch. The nickel production is insanely sensitive to sunlight. A tiny change in heat, and it just shuts off. This on-off behavior points to a parent molecule with a sharp decomposition threshold. The only candidate that fits is nickel tetracarbonyl, a compound with the chemical formula NiCO4, where nickel is bonded to 4 carbon monoxide groups. This is not a naturally occurring compound. We synthesize it on Earth using the Mond process, passing carbon monoxide over impure nickel at controlled temperatures to produce a volatile compound that later decomposes back into pure nickel and carbon monoxide. It's an industrial chemical. It's how we refine nickel to extreme purity for electroplating and catalysis. And according to the Post, it's what's coming off the surface of an object that supposedly has been frozen in interstellar space for billions of years. What the hell, the author asks, is a synthetic industrial chemical doing on a rock which we think has been in space for billions of years? Fifth, the thermal anomaly. At perihelion, 3I Atlas was absorbing about 15 gigawatts of solar energy, enough to power a small city. At that distance from the sun, that amount of energy should be driving massive water sublimation. The surface should be boiling, but water makes up only 4% of the outgassing. The object has somehow found a way to either dispose of or regulate an enormous thermal load to keep its surface locked at a specific low temperature. This is not how passive bodies behave. You heat ice, it melts or sublimates. You heat rock. It radiates the energy away, according to blackbody radiation laws, reaching an equilibrium temperature determined by absorbed solar energy and infrared emission. You don't get thermal regulation without an active system, something moving heat from one place to another, something managing energy flow. The Post continues with more anomalies. The object's trajectory is too perfect, bringing it past multiple planets with timing that placed perihelion behind the sun from Earth's viewpoint. The dust being shed has polarization properties unlike any known natural material. There's a faint anti-tail pointing toward the sun that requires a powerful directional jet, but the object's brightness doesn't vary, suggesting either no rotation or a perfectly uniform outgassing envelope. Each paradox is a wall.
the Post states, and we are all standing here, staring at the walls, refusing to see the shape of the room. So what is the shape of the room? What single explanation makes all of this coherent? The anonymous researcher offers one 3-eye atlas is a macroscopic quantum object, a cue ball, a stable massive particle left over from the first microseconds after the Big Bang, a bubble of different physics that has managed to survive cloaked in a skin of normal matter accreted over billions of years. This is not science fiction, the Post insists. Cue balls are predicted by certain supersymmetric field theories. They're a candidate for dark matter. And if they exist, they've been drifting through the galaxy, invisible and undetectable, until one happened to pass close enough to a star that its outer icy shell began to sublimate. The Post ends with two testable predictions. First, keep watching as 3-eye atlas recedes from the sun. A normal comet's activity is driven by solar heating. As it moves farther away, it should fade and die. But if 3-eye atlas has an internal energy source, if it's a cue ball with its own power supply, the brightness and outgassing rate will remain impossibly high even in the outer solar system, violating every model of passive thermal evolution. Second point, a gamma-ray telescope at it. A cue ball's decay isn't silent. It's a constant particle physics event producing high-energy photons. If you detect a stable, non-thermal gamma-ray signature that can't be attributed to solar-wind interaction, you're not seeing a comet. You're hearing the heartbeat of an object that does not follow the rules. December 19th, we'll test the first prediction partially. We'll see if the debris cloud exists. But the gamma-ray prediction requires someone to actually point a telescope and look. As of November, no gamma-ray observatory has publicly announced observations of 3-eye atlas. The Post has been screenshot, archived, and disseminated across scientific forums and social media. Some dismiss it as an elaborate hoax, too convenient, too detailed, too perfectly aligned with existing speculation about Oumuamua's unusual properties. Others point out that hoaxers don't typically make falsifiable predictions with specific timelines. Real science proceeds by testing hypotheses against observation. If the predictions fail, the hypothesis fails. Clean, simple, definitive. We don't know who wrote it. We may never know. The anonymity that makes the Post suspicious also makes it impossible to dismiss based on credentials or affiliation. The ideas stand or fall on their merits judged solely by how well they match reality, which is arguably how science should always work. There's an old saying among researchers, all models are wrong, but some are useful. The question isn't whether the cue ball hypothesis is correct. We don't have nearly enough data to say that. The question is whether it's useful, whether it organizes the observations into a coherent picture, whether it makes predictions that help us understand what we're seeing, and most importantly, whether it's worth testing. Because if someone doesn't point a gamma-ray telescope at 3-eye atlas in the next few months, we may never know. The object is leaving. By late 2026, it will be too faint for most observations. By the end of the decade, it will be gone back into the darkness from which it came. The universe has handed us an anomaly on a countdown timer. We can study it, or we can let it slip away. But we can't do both half-heartedly and expect answers. The hoofbeats continue. The question is whether we're brave enough or curious enough to look and see what's making them. There's a particular pleasure in spectroscopy that other branches of astronomy don't quite capture. When you image a distant galaxy or photograph a nebula, you're seeing the universe in its visual glory. The sweep of spiral arms, the delicate filaments of shocked gas, the stark beauty of cosmic architecture. But spectroscopy is different. Spectroscopy lets you taste the universe. When light passes through a prism or diffraction grating, it spreads into its component colors, the rainbow spectrum from red through violet. But that rainbow isn't smooth. It's interrupted by dark lines where specific wavelengths are missing, absorbed by atoms and molecules in the object's atmosphere or surrounding gas. Each element and compound has its own unique pattern of lines, a fingerprint as distinctive as human DNA. Point a spectrograph at a distant star and you can identify iron, calcium, magnesium, hydrogen, even though that star is trillions of kilometers away, and you will never touch it, never sample it, never visit it. The light itself carries the information encoded in which wavelengths are present and which are missing. This is how we know what 3I Atlas is made of. This is how we taste its chemistry, and what we're tasting is wrong. The first careful spectra came from the W.M. Keck Observatory in Hawaii, one of the largest optical telescopes in the world, with a mirror 10 meters across, collecting light with exquisite sensitivity. When astronomers turned Keck's spectrograph toward 3I Atlas, they saw emission lines characteristic of a comet, carbon dioxide, carbon monoxide, cyanide, various organic molecules. Expected. Standard. But they also saw nickel. Lots of nickel. Strong emission lines in the green part of the spectrum glowing brightly as solar ultraviolet light ionized nickel atoms in the coma, and they cascaded back down through energy levels, releasing photons at characteristic wavelengths. Nickel isn't unknown in comets. Most solar system comets show trace amounts of metallic emission sodium iron, nickel magnesium released when dust grains are vaporized by sunlight or when refractory particles embedded in ice are freed as the ice sublimates. But it's always trace amounts, parts per million, background noise compared to the dominant volatiles like water and carbon dioxide. 3I Atlas was different. The nickel emission was strong, dominant, comparable to or exceeding the carbon-bearing molecules, and when astronomers looked for iron emission, which should be even stronger than nickel because iron is more abundant in cosmic material, they found nothing. Iron lines that should have been prominent in the spectrum were absent, below detection limits. This is deeply strange. In our solar system, in the meteorites that fall to Earth, in the asteroids we've visited with spacecraft, in the very composition of our planet's core, nickel and iron occur together in roughly constant proportions, about 6% nickel relative to iron by mass. This ratio reflects how these elements were made in supernova explosions, forged when massive stars collapsed and scattered their nuclear ashes across the galaxy. When protoplanetary disks condensed from interstellar clouds, they inherited this ratio. When planets and asteroids and comets formed, they inherited it too. You don't get nickel without iron unless something has actively separated them. And there aren't many natural processes that do that. But there is an industrial process, one we've been using on Earth for over a century. In 1890, a German-British chemist named Ludwig Mond was working on refining nickel ore. Nickel is valuable, strong, resistant to corrosion, essential for steel alloys and electroplating. But extracting pure nickel from ore is challenging because it's chemically similar to iron and other metals. Traditional smelting gives you impure metal. Mond discovered something remarkable. When he passed carbon monoxide gas over impure nickel at temperatures around 50-60 degrees Celsius, the nickel reacted to form a volatile compound nickel tetracarbonyl NiCO4. This compound is a liquid at room temperature but vaporizes easily. You can capture the vapor, then heat it to higher temperatures around 200 degrees Celsius, and it decomposes back into pure nickel metal and carbon monoxide gas. The Mond process became the standard method for producing high-purity nickel. It's elegant, efficient, and produces nickel with purity exceeding 99.9%. Iron doesn't form a stable tetracarbonyl under the same conditions, so it stays behind. The process naturally separates nickel from iron. But nickel tetracarbonyl is not a natural compound. It doesn't form in volcanic gases on Earth. It doesn't form in hydrothermal vents or biological systems. It requires specific conditions, the presence of carbon monoxide at precisely calibrated temperatures and pressures that don't occur spontaneously in terrestrial environments. Could it form in space? Possibly. Interstellar clouds contain carbon monoxide. They contain nickel atoms either free or as tiny grains. If conditions were right, cold enough, dense enough, with appropriate chemical pathways, perhaps nickel tetracarbonyl could condense onto dust grains and be incorporated into comets during their formation billions of years ago in the protoplanetary disk of another star. But here's the thing, nickel tetracarbonyl is exquisitely sensitive to temperature. It's stable in a narrow range. Too cold and it freezes solid. Too hot and it decomposes. The observations of 3I Atlas show that nickel emission is highly variable with sunlight turning on and off sharply as solar heating changes. Small temperature variations cause large changes in nickel production. This on-off behavior is exactly what you'd expect from a compound with a sharp thermal stability window. It's not what you expect from ordinary sublimation of ice or thermal decomposition of refractory grains, which change gradually as temperature increases. The sharpness of the transition suggests a parent molecule decomposing at a threshold temperature. Nickel tetracarbonyl fits. Nothing else fits nearly as well. But if nickel tetracarbonyl is present on 3I Atlas, where did it come from? If it can't form naturally on Earth, if it requires industrial processes, or at minimum very specific chemical conditions, how did it end up on a comet that supposedly formed in another star system billions of years ago and has been frozen in interstellar space ever since? One possibility we're wrong about natural formation pathways. Maybe there are astrophysical environments where nickel tetracarbonyl forms routinely. Cold, dense molecular clouds with unusual chemistry. Regions near young stars where carbon monoxide is abundant and nickel grains are being processed by radiation. We've never directly detected nickel tetracarbonyl in space, but our spectroscopic surveys of interstellar molecules are far from complete. If this is true, 3I Atlas is giving us a window into chemistry that doesn't occur in our solar system, truly alien chemistry, in the sense of formed under different conditions in a different stellar environment. That would be scientifically fascinating. It would tell us that planet formation is more chemically diverse than our single star sample suggests. It would expand our understanding of what's possible in protoplanetary disks. But there's another possibility, one that makes people uncomfortable. What if the nickel tetracarbonyl isn't accidental? What if it's deliberate? If you were designing a long-duration probe meant to survive in interstellar space for millions or billions of years, you'd need materials that are stable, lightweight, and resistant to radiation. Metals are strong but heavy. Organic polymers degrade under ultraviolet light and cosmic rays. Ice is abundant but sublimates. Ideally, you'd want something that can self-repair, something that regenerates its surface as material is lost. Nickel tetracarbonyl, despite being toxic to humans, has interesting properties from an engineering standpoint. It can be synthesized from simple starting materials, nickel and carbon monoxide, both of which are available in space. You could design a system that continuously coats nickel surfaces with carbonyl layers, creating a protective shell that renews itself as it's eroded. This is speculation, obviously, but it's the kind of thing an advanced technology might do if it needed durable materials for interstellar voyages. The dust coming off 3I Atlas has been described by the anonymous 4chan post as manufactured material black and porous as smoke, large, incredibly complex particles, not sand, not ice, something engineered. If true, if the dust isn't just aggregates of natural grains, but actual structured material, then the chemistry starts to look less like an accident and more like a design choice. Let's continue with the other chemical anomalies, because nickel is only the beginning. Carbon dioxide dominates the outgassing 87% by mass, compared to water's 4%. This inverted ratio is unprecedented among solar system comets. Water ice condenses at higher temperatures than carbon dioxide ice. In a protoplanetary disk, water ice forms closer to the star carbon dioxide ice farther out. Comets that form in the colder regions will have more carbon dioxide relative to water, but never to this extreme. If 3I Atlas formed so far from its parent star that carbon dioxide vastly dominates, implying formation distances beyond even our solar system's Kuiper belt, it should be ancient and pristine. It should never have been heated significantly because heating drives off the more volatile carbon dioxide first. But 3I Atlas is actively outgassing at 150 kilograms per second. That's not the behavior of a pristine object on its first pass near a star. That's vigorous activity suggesting either the object is much larger than estimated with enough thermal mass to retain volatiles even after previous heating, or the activity is driven by something other than passive solar heating. Then there's the cyanide to nickel ratio. Cyanide hydrogen cyanide, or cyanogen, is a standard comet volatile formed from reactions involving nitrogen and carbon compounds in the protoplanetary disk. Every comet has some, but the ratio of cyanide to other species gives clues about formation chemistry. In 2I Borisov, the only other interstellar comet we've studied in detail, the cyanide abundances and metal ratios were unusual, but still within orders of magnitude of solar system comets. Different, yes, but recognizably similar. 3I Atlas has a cyanide to nickel ratio that's orders of magnitude off from Borisov. If both are coming from sublimation of pristine ice, this suggests wildly different formation chemistry. Or it suggests they're not both coming from sublimation of ice. Perhaps one component is coming from a different source, decomposition of a compound ablation of internal material, something that alters the expected ratios. And finally, the dust. When light scatters off dust particles, it becomes polarized. The electric field vibrations align preferentially in certain directions, depending on the size, shape, and composition of the particles. By measuring the degree and sign of polarization, you can infer properties of the dust grains. Most comets show positive polarization in the range of a few percent, consistent with irregular grains of silicates, organics, and ices scattering light according to well-understood Mi theory. 3I Atlas shows extreme negative polarization, 2.7% at a phase angle of 7 degrees. This is unprecedented. No known comet, including Borisov, has shown polarization this negative. To produce extreme negative polarization, dust particles need very specific optical properties. They need to be large compared to the wavelength of light. They need to be highly porous, mostly empty space with complicated internal structure. Think of fractal aggregates. Clusters of tiny grains creating a hierarchy of voids and solid material that causes light to scatter in counterintuitive ways. Nature can make such structures through coagulation in the coma. Small grains collide and stick together electrostatically, building up fluffy aggregates. But the degree of negative polarization in 3I Atlas is at the extreme edge of what fractal models can explain. It's almost as if the dust is optimized for this specific optical property. Optimized for what purpose? If natural, none, it's just an accident of formation and coagulation physics. But if engineered, extreme porosity and complex structure are exactly what you'd want for thermal insulation and radiation shielding, low density, high surface area, efficient at scattering radiation across a broad spectrum, aerogels. The ultralight foams used in spacecraft insulation have similar properties. Carbon nanofoam, with its fractal pore structure, produces extreme optical effects. If you were designing a lightweight, durable, multifunctional material for an interstellar probe's exterior, you might end up with something whose dust, when shed, would show exactly these polarization characteristics. Is this proof nature is clever? Nature has had billions of years and countless trillions of comets to experiment with different structures and chemistries. What looks optimized might just be rare. But when you have nickel, without iron carbon dioxide, without water dust, with extreme polarization, and compounds that on Earth we only make industrially, all on the same object, you start to wonder whether you're looking at a collection of low-probability accidents or a single high-probability design. The chemistry of 3I Atlas is a message. Whether that message is, I formed in very unusual conditions, or I was built for a purpose, we don't yet know. But the universe is speaking in the language of spectral lines and molecular abundances, and we would do well to listen carefully. December will bring better data, higher resolution spectra from Hubble and Webb, more careful measurements of the dust properties, confirmation or refutation of the nickel tetracarbonyl hypothesis through detailed modeling of the temperature-dependent emission. Until then, we're left with a taste, a chemical fingerprint that doesn't quite match anything we've sampled before. And the lingering question: when something tastes this strange, do you assume it's just an exotic vintage, or do you start wondering whether someone mixed the drink deliberately? Avi Loeb is not a fringe scientist. This bears repeating because in the discourse around 3I Atlas, his name comes up often, usually accompanied by either admiration or exasperation, depending on who's speaking. Loeb is the Frank B. Baird Jr. Professor of Science at Harvard University, one of the most prestigious endowed chairs in academia. He's published over 800 peer-reviewed papers. He served as chair of Harvard's astronomy department, as director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics, as chair of the board on physics and astronomy of the National Academies. His work spans cosmology, black hole physics, the first stars, and the search for extraterrestrial intelligence. When Loeb says something, it carries weight. Not infallible weight. Science doesn't work by authority, but the weight of a career spent doing rigorous work, publishing results that withstand scrutiny and training generations of researchers. And Loeb has compiled a list, 10 anomalies of 3I Atlas. Each one taken alone might be explicable. Together, they form a pattern that's difficult to dismiss. Let's walk through them one by one and understand why each one makes this object increasingly difficult to explain as a natural comet. Anomaly. 1 retrograde trajectory, aligned within 5 degrees of the ecliptic plane. We covered this earlier, but let's quantify it properly. The ecliptic is the plane defined by Earth's orbit around the Sun. The major planets all orbit within a few degrees of this plane because they formed from a rotating disk of gas and dust, the protoplanetary disk that surrounded the young Sun 4.6 billion years ago. Objects originating in our solar system tend to stay near the ecliptic because that's where they were born. But comets from the Oort cloud, the spherical shell of icy bodies extending halfway to the nearest star, come from all directions. There's no preferred plane. They should arrive with inclinations uniformly distributed across the sky. An interstellar object ejected from some other star system should also arrive from a random direction. It spent millions or billions of years crossing the galaxy. Subject to the gravitational perturbations of stars, it passed until by chance its trajectory intersected ours. No mechanism selects for trajectories aligned with our ecliptic. Yet 3I Atlas is within 5 degrees. It's moving in our planetary plane just backward. The solid angle within 5 degrees of the ecliptic represents about 0.2% of the full sky, 1 in 500. Not impossible, but improbable enough to notice. Anomaly. 2 sunward anti-tail confirmed by spectroscopy. Most comet tails point away from the sun, pushed by solar radiation pressure on dust particles and by the solar wind carrying ionized gas outward. Sometimes you can see an apparent anti-tail, a spike pointing sunward, but these are usually optical illusions.
You're viewing the comet's dust trail edge on, and perspective makes it appear to point toward the sun even though it doesn't. 3I Atlas has a real anti-tail. Multiple telescopes, including Hubble and the Keck Observatory, have confirmed this through spectroscopy and geometry analysis. There is actual material being ejected toward the sun. To do this requires a powerful jet on the sun-facing side blasting gas and dust sunward with enough velocity to overcome radiation pressure. Carbon dioxide jets can do this. They create high-pressure outflows that can lift heavy particles. Fine. but jets come from localized active regions on the nucleus where ice is exposed to sunlight. As the nucleus rotates, these active regions turn into and out of sunlight, creating periodic variations in brightness and coma shape. You see pulses. You see the jet turn on, turn off, sweep around as the nucleus spins. Multiple observatories watched 3I Atlas for days during its active period.
Its brightness remained constant. No variations, no pulses, a flat line. If there's a jet powerful enough to create the anti-tail, and if that jet is tied to a surface feature, and if the nucleus is rotating, which all comets do, there should be a brightness rhythm. The absence of that rhythm means either the nucleus isn't rotating dynamically unusual for an object that's been tumbling through space for billions of years, or the outgassing is somehow uniform across the entire sun-facing hemisphere. Neither explanation is satisfying for a natural comet anomaly, 3 mass and velocity exceeding predecessors by factors of thousands. Oumuamua 100 meters, 26 kilometers relative to the Sun. Borisov 400 meters, 32 kilometers. 3I Atlas 5,000 meters, minimum 60 kilometers. Each object is larger and faster than the last. Size distributions in nature, whether asteroids, moons, or pieces of debris, follow power laws, where small objects vastly outnumber large ones. Every survey confirms this: a few big rocks, many small rocks. If you're sampling randomly, you should find small objects more often. Finding a giant in your third detection is like reaching into a bag of marbles where there are 1,000 small marbles and 1 large marble and pulling out the large marble on your third try. Possible, yes. Suggestive of non-random sampling. Also yes. Combined probability. Assuming independent random sampling from a typical size distribution less than 0.1%. Anomaly. 4. Arrival timing optimized for planetary encounters. October 3rd past Mars at 29 million kilometers. November 3rd past Venus at 97 million kilometers. March 2026 will pass Jupiter. 3 major planets encountered within 6 months. For a reconnaissance mission, this trajectory is ideal. You fly past multiple worlds in quick succession, gathering data on each before departing the system. Additionally, perihelion occurred during solar conjunction from Earth. For 2 weeks in late October, 3rd Atlas was unobservable by ground-based telescopes because it was behind the Sun from our perspective. If you wanted to perform a maneuver or operation without being watched by the most technologically advanced planet in the system, this is when you do it. The probability of arrival timing placing perihelion during solar conjunction roughly 25% depending on the length of the conjunction period. The probability of passing within the observed distances of 3 major planets, roughly 0.02% accounting for the geometry and the fact that planets move. Combined, about 0.05%, 1 in 20,000. Anomaly. 5 nickel exceeds iron by orders of magnitude. We discussed this in the previous chapter. Nickel and iron should occur together in cosmic abundance ratios about 6% nickel to iron by mass. Every meteorite, every asteroid, every primitive solar system sample confirms this ratio with remarkable consistency.
3I Atlas has strong nickel emission and no detectable iron. To get this requires either a source region with vastly different stellar nucleosynthesis possible but rare, or a process that selectively separates nickel from iron, such as formation of volatile nickel tetracarbonyl or material that was never part of a normal protoplanetary disk in the first place. Probability that an interstellar comet would naturally have this chemistry less than 1% based on surveys of solar system comets, and the expectation that planetary chemistry should be broadly similar across stellar systems. Anomaly. 6. Water content only 4% by mass. Normal comets, 50–80% water ice. 3I Atlas 4% water, 87% carbon dioxide. This inversion suggests formation in extremely cold conditions far beyond where most comets form.
But if the object formed that far out and has remained pristine, why is it so actively outgassing now if it has been heated before? Why does it still have so much of the more volatile carbon dioxide? The thermal history required to produce this composition, while maintaining high activity, is difficult to construct within standard comet formation and evolution models. Anomaly 7. Extreme negative polarization unprecedented among comets. Polarization at 7 degrees phase angle, 2.7%. For comparison, Borisov showed polarization in the typical range for comets. No solar system comet has shown polarization this extreme. To produce it requires dust with very specific properties, large porous fractal structure. Nature can make fractal aggregates through coagulation, but reaching this level of negative polarization pushes the limits of models. It's at the extreme edge of what we can explain with natural dust aggregation processes. Probability less than 1% based on surveys of comet dust properties. Anomaly 8. Arrival direction within 9 degrees of the 1977 WOW signal. In August 1977, the Big Ear radio telescope in Ohio detected a strong narrowband signal at 1420 MHz close to the hydrogen line, a frequency that SETI researchers consider promising for interstellar communication because hydrogen is the most abundant element in the universe. The signal lasted 72 seconds and was never detected again, despite follow-up observations. It remains unexplained. Most likely it was terrestrial interference or a transient astrophysical source, but it achieved fame because of how closely it matched what SETI researchers expected an extraterrestrial transmission might look like. The signal came from a region in Sagittarius. When you trace 3I Atlas's trajectory backward through the galaxy, accounting for its velocity and direction, it originates from a region within 9 degrees of the WOW signal source.
9 degrees is not a precise alignment. It's a fairly large area on the sky, and the odds of any random direction on the sky being within 9 degrees of any specific target is about 0.6%. Is there a connection? Almost certainly not. The WOW signal was likely noise, and even if it wasn't, the probability that the same civilization would send both a radio transmission and a physical probe, and that both would arrive at Earth within 50 years of each other, is vanishingly small. But coincidences accumulate, and 0.6% is 0.6% anomaly. 9. Rapid brightening and unusual color near perihelion. Solar observatory data suggests 3I Atlas brightened near perihelion with a power law dependence roughly as 1 over distance to the 7.5 power. Normal comets brighten more gradually, typically as 1 over distance squared or cubed. Additionally, there are preliminary unconfirmed reports that the object's color appeared closer to solar or even blue shifted rather than the typical reddish color of comets. If real, this would require either massive ionization producing blue emission lines or a thermal source hotter than expected. These observations are difficult to interpret because solar observatories aren't designed for precision photometry of faint comets. Image processing artifacts are likely, but the reports exist and they're consistent with something unusual happening near perihelion. Anomaly. 10. Non-gravitational acceleration without corresponding debris cloud. This is the anomaly still being tested. The acceleration is confirmed. JPL Horizon's data and ALMA observations both show it. But the debris cloud that should result from ejecting billions of tons of gas has not yet been observed because we haven't had a clear view since perihelion. December 19th settles this. If the cloud is there massive and obvious, then the acceleration has a natural explanation and this anomaly disappears. If the cloud is absent or much smaller than required, then we're missing something fundamental. Now let's do the uncomfortable math. Each of these anomalies has an associated probability, the odds that a random natural object would display that property. If the anomalies were independent, you'd multiply the probabilities. 0.02 x, 0.06 x, 0.01 x, 0.05 x, 0.1 x, 0.1 x, 0.1 x, 0.6 x cubed.
The product would be an absurdly small number. Something like 10 to 1 or 15 or worse. 1 in a quadrillion, but the anomalies aren't independent. The trajectory affects arrival timing, the composition affects brightness and chemistry. You can't just multiply them and claim the result is meaningful without accounting for correlations. Still, even being generous and assuming significant correlations, the joint probability is very low. How low depends on how you model the dependencies, but it's clear that 3I Atlas is not a typical interstellar object. This brings us to Bayesian reasoning, a framework for updating beliefs based on evidence. You start with a prior probability. Before seeing any data, what are the odds that an interstellar object is artificial or exotic? Most people would say very low, maybe 1 in a million, maybe 1 in a billion. Then you see data that's unlikely given the natural hypothesis. You update your probability using Bayes' theorem. The posterior probability, your belief after seeing the evidence, shifts. It might not shift enough to make the alternative hypothesis likely. Starting from 1 in a billion odds, even strong evidence might only move you to 1 in 1,000. Still improbable, but no longer absurd. The point isn't to conclude that 3I Atlas is artificial. The point is that the data warrants serious consideration of alternatives to the standard model. When you have 10 anomalies each individually unusual, and they all point in the same general direction toward properties that would make sense for an exotic object or a designed object, you can't just wave your hand and say, "It's a weird comet." Science advances by asking whether the data fits the hypothesis. Right now, the natural comet hypothesis is straining. It's not broken. We can still construct scenarios where all of this is natural, but it requires a lot of fine-tuning, a lot of rare conditions all applying to the same object. Occam's razor cuts both ways. Sometimes the simplest explanation is, it's natural but unusual. Sometimes the simplest explanation is, our assumptions about what's possible are incomplete. We don't know yet which applies to 3I Atlas, but we're about to find out. Let's take a breath. Let's step back from the speculation and the tantalizing anomalies and ask the most important question in science. What's the simplest explanation that fits the data? Not the sexiest explanation, not the one that gets headlines or starts arguments at conferences. The simplest, the one that requires the fewest new assumptions, the fewest violations of what we already know. For 3I Atlas, the simplest explanation is this: it's a comet. A very unusual comet with properties we haven't seen before, formed under rare conditions in a stellar system with chemistry different from our own. Strange, yes. Unprecedented, absolutely, but fundamentally natural. Let's build this case carefully, because if we're going to reject it, we need to understand exactly what we're rejecting and why. Start with formation. 3I Atlas came from somewhere, some protoplanetary disk around a star, perhaps hundreds of light years away, billions of years ago. That disk had gas and dust heated by the young star, with temperature decreasing as you moved outward. Close to the star, rocky planets. Farther out, gas giants. Still farther, ice giants and small icy bodies. Water ice condenses at relatively high temperatures well within the frost line where volatiles begin to freeze. Carbon dioxide ice requires colder conditions farther from the star. If 3I Atlas formed very far out in the cold, distant reaches of its system's equivalent of the Kuiper Belt, or even farther, it would naturally have more carbon dioxide relative to water. How far out? To get an 87:4 ratio, you'd need formation temperatures perhaps around 30 Kelvin, or colder in regions where carbon dioxide is the dominant condensing volatile because water has already frozen out closer in and isn't abundant this far from the star. This is beyond where most comets form in our solar system, but not impossible. Some stellar systems have more extended disks. Some have different thermal structures depending on the star's luminosity and the disk's opacity. So formation in an unusually cold, distant region of a protoplanetary disk. Rare, but plausible. Now address the mass. If 3I Atlas is truly 33 billion tons or more in a 3 to 5 kilometer sphere, it's dense.
far denser than typical comets, which are porous, fluffy mixtures of ice and dust with bulk densities around 0.5 grams per cubic centimeter, half the density of water. But not all comets are fluffy. Some of the nuclei we visited with spacecraft show surprising density variations, regions of consolidated material, compacted layers. If 3I Atlas experienced collisions during its formation, or if it underwent significant heating at some point perhaps. By passing close to its parent star, before ejection, its interior could be compacted. Ice sintered into denser forms. Voids collapsed. A density of 23 GCM3 is high for a comet, but not impossible if the object is mostly rock and metal with ice filling the pores. This would make it more like an asteroid with an icy coating than a traditional comet, but we know the boundary between asteroids and comets is fuzzy. We have objects like Phaethon classified as an asteroid, but suspected to be an extinct comet nucleus. The distinction is observational, not fundamental. So unusually high density from either compaction or high rock-to-ice ratio. Rare, but plausible. The nickel-iron problem is trickier, but not insurmountable. Stellar nucleosynthesis produces elements in certain ratios, but those ratios can be modified by subsequent processing. If 3I Atlas formed from material enriched in supernova ejecta, if its parent system happened to form in a region where a recent supernova had seeded the interstellar medium with fresh, heavy elements, the elemental abundances could be skewed. Different types of supernovae produce different element ratios. A core collapse supernova from a massive star ejects material processed through different nuclear burning stages, each with its own abundance pattern. It's possible, unlikely, but possible that the material that formed 3I Atlas came from an environment with naturally high nickel-to-iron ratios. Alternatively, the iron could be present but not appearing in the spectrum. If iron is tied up in non-volatile grains buried beneath the surface, or if it's in chemical forms that don't sublime easily, it wouldn't show up in emission even though it's there. The nickel might be in a volatile form, say naturally formed nickel tetracarbonyl produced by some exotic chemistry we don't understand yet, while iron remains locked in refractory minerals. We're stretching here. This requires multiple fortuitous circumstances, but it's not impossible. So unusual nickel-iron ratio from either atypical nucleosynthesis or differential volatility. Rare, but plausible. What about the thermal behavior? Why isn't 3I Atlas boiling off more water when it's absorbing gigawatts of solar energy? If the object is large and massive, it has significant thermal inertia. Heat doesn't penetrate quickly. The surface layer might be sublimating, but the interior remains cold, insulated by overlying material. The outgassing we see is from a thin active layer, while the bulk of the comet stays frozen. Additionally, if the surface has developed a crust, a layer of non-volatile residue left behind, as ice sublimates, this crust acts as thermal insulation. We've seen crusts on solar system comets. They slow down heat penetration and reduce sublimation rates. A thick, well-developed crust on a large comet could explain why water isn't dominating the outgassing even near perihelion. So thermal regulation through size, thermal inertia, and insulating crust. Not typical, but within the bounds of comet physics. The nickel tetracarbonyl issue is the biggest chemical puzzle, but even here we can construct natural pathways. Cold molecular clouds are chemically rich environments. Carbon monoxide is abundant. Nickel atoms and grains are present. Laboratory experiments have shown that at very low temperatures, with appropriate catalysts or radiation processing, you can form organometallic compounds that don't form under terrestrial conditions. It's speculative, but imagine a cold, dense cloud where UV radiation from nearby stars is dissociating molecules and creating reactive radicals. Nickel atoms are tiny nickel grains coated with carbon monoxide ice, processed by UV photons over millions of years, might produce nickel carbonyl compounds that get incorporated into dust grains. When those grains accrete into comets, the compounds come along.
We've never detected nickel tetracarbonyl in space, but we've never specifically looked for it. Our spectroscopic surveys of interstellar molecules are biased towards simple species that are abundant and easy to detect. Complex organometallics with weak spectral features could be present but overlooked. So nickel tetracarbonyl from exotic but natural interstellar chemistry, highly speculative but not physically impossible. The dust polarization can be explained by hierarchical aggregation. Small grains collide in the coma, sticking together through electrostatic forces and van der Waals interactions. These aggregates collide with other aggregates, building up fractal structures. Clusters of clusters with voids and complexity at every scale. Computer simulations of this process show that you can produce aggregates with optical properties approaching what 3i Atlas displays. The extreme negative polarization requires pushing the aggregation to high levels of complexity, and the structures need to be somewhat fragile, high porosity, low compaction, but it's achievable. Different comets might produce different levels of aggregation depending on their outgassing rates, the dust-to-gas ratio, the electrostatic environment in the coma, and how long the dust spends in the coma before dispersing. 3i Atlas could simply be at the extreme end of this distribution, the comet that happened to produce the most elaborate fractal aggregates. So extreme dust polarization from unusually efficient hierarchical aggregation, rare but plausible. The trajectory and timing are harder to explain naturally but not impossible. The ecliptic alignment is low probability, 0.2%, but not prohibitively so. 1 in 500 objects should arrive roughly in the ecliptic. We found 3 interstellar objects. Drawing one with this property isn't shocking. The planetary encounter timing is more striking, 0.005% probability, but you have to be careful with statistics. We're selecting the object because it's interesting. If 3i Atlas had passed nowhere near any planets, we probably wouldn't be paying as much attention, and we wouldn't be calculating probabilities for it. This is a mild form of selection bias. We notice the unusual cases. Moreover, Earth and the other planets occupy substantial lanes in the ecliptic. An object traveling retrograde in the ecliptic will naturally pass near whichever planets happen to be in its path. The timing that looks optimized might just be geometry. So trajectory and timing from selection bias and geometric coincidence. Uncomfortable, but possible. The anti-tail without brightness variation is perplexing, but perhaps the nucleus is in a rare rotational state. If it's tumbling chaotically, rather than spinning smoothly, a state called excited rotation, the orientation might change slowly enough that brightness variations are smeared out over longer periods than we observed. Or if the nucleus is elongated and we're viewing it nearly pole-on, we might not see much brightness change even if it's spinning. The jet creating the anti-tail could be from a single large active region positioned favorably, or from multiple regions that happen to have similar activity levels, producing a net sunward push without strong periodic variation. So, anti-tail without variation from unusual rotation state and geometric viewing angle. Unlikely, but not impossible. The acceleration with perfect in-plane confinement, A3-0, is the anomaly that strains the natural explanation most severely. For 20 days of thrust with no out-of-plane component, you need either perfect symmetry jets arranged to cancel vertical forces or some mechanism we don't understand. But here's a thought. What if the horizon solution is premature? The orbital determination for 3i Atlas is based on observations covering a limited time span, much of it during perihelion, when the object was difficult to observe. The A3-0 result might be an artifact of limited data. As more observations come in, especially the high-quality astrometry from the December flyby and the IAWN monitoring campaign, the solution might change. We might find that A3 is actually non-zero but small, or that the acceleration model needs refinement. Orbital solutions evolve as data accumulates. Early solutions for asteroids and comets are often revised significantly as more observations constrain the orbit better. Declaring A3-0 significant based on a preliminary solution might be premature, so in-plane acceleration from incomplete orbital solution that will be refined. Tentative but defensible. Finally, the debris cloud. This is the test. If the cloud is there in December, the natural explanation survives. The outgassing was real, the mass ejection was real, and all the anomalies, while unusual, can be accommodated within the framework of exotic but natural comet physics. We'd have an object that formed in rare conditions with unusual chemistry, large size, and improbable trajectory. Each of those is individually unlikely, but the universe is vast. Billions of stars, billions of planetary systems, billions of comets ejected into interstellar space over billions of years. With that many trials, even very unlikely combinations occur occasionally. We found 3I Atlas quickly because it's large and active, easier to detect than smaller, fainter objects. Selection bias favors us finding the unusual ones early. This is the exotic comet hypothesis. It requires multiple rare conditions, but no new physics, no exotic matter, no technology. Just nature being more creative than our limited sample of solar system comets had led us to expect. It's a defensible position. Arguably, it's the position that Occam's razor prefers. Don't multiply entities beyond necessity. If you can explain the observations with known physics applied to unusual but possible conditions, that's better than invoking unknowns. But here's the discomfort: better doesn't mean we correct. History is full of examples where the simpler explanation turned out to be wrong because nature had a surprise waiting. Continental drift seemed more complicated than stable continents until we discovered plate tectonics. The idea that ulcers were caused by bacteria seemed more convoluted than stress-induced acid until Helicobacter pylori was isolated and proven. Fast radio bursts were dismissed as instrumental artifacts because natural astrophysical transients seemed unlikely until they were confirmed beyond doubt. Sometimes nature is simpler than we think.
Sometimes it's weirder. The exotic comet hypothesis will stand or fall on the December observations. If the debris cloud is there, this hypothesis wins, and 3I Atlas becomes a fascinating case study in how diverse comet properties can be when you sample from other stellar systems. If the debris cloud is absent, we move to the alternatives, and those alternatives require us to rethink what we thought we knew about the universe. Now we enter stranger territory.
Not speculative in the sense of making things up, but speculative in the sense of discussing physics that's mathematically consistent, predicted by certain theories, but never observed. Physics that lives on the boundary between should exist and probably doesn't, but maybe. Welcome to the cue ball hypothesis. Let's start at the beginning, literally, the very beginning. The Big Bang. In the first moments after the universe began, everything was hot beyond comprehension. Temperatures trillions of degrees. Energies high enough that the four fundamental forces we experience today, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, were unified into a single force. The physics governing that early universe is different from the physics we experience now, just as ice water and steam are different phases of the same substance. As the universe expanded, it cooled, and as it cooled, symmetries broke. Symmetry breaking is a phase transition like water freezing. At high temperatures, water molecules move freely in all directions. The system is symmetric with no preferred orientation. When water freezes, that symmetry breaks ice, has a crystal structure with preferred directions. The phase transition from liquid to solid changes the symmetry. Similarly, as the universe cooled, the unified force split into separate forces. First, gravity separated, then the strong nuclear force. Then, the electromagnetic and weak forces split at energies around 100 GeV, about a trillionth of a second after the Big Bang. During these phase transitions, fields that permeate all of space settled into new configurations. Most of the time, fields relax smoothly into their lowest energy state, the vacuum we inhabit now. But sometimes, in certain theories, fields can get trapped in metastable states, local energy minima, that aren't the absolute lowest energy, but are stable enough to persist. Imagine a ball sitting in a valley on a hillside. It's not at the bottom of the hill, but it's in a depression. It's stable as long as nothing pushes it over the edge. Given enough time or enough random fluctuations, it might eventually roll down to the true lowest point. But if the valley is deep enough and the surrounding hills are high enough, it could sit there for a very, very long time. In certain extensions of the Standard Model, particularly supersymmetric theories, there are scalar fields that can form stable lumps called solitons. These aren't particles in the traditional sense. They're localized configurations of a field held together by the field's own dynamics. Topological solitons get their stability from topological properties, the way the field wraps around itself in a manner that can't be unwound without tearing. But there's another type, non-topological solitons or cue balls, stabilized by conserved quantum numbers. Here's the idea. Imagine a scalar field that carries a charge, not electric charge necessarily, but some other conserved quantum number associated with a symmetry of the theory. If you have a large lump of this field all oscillating in phase, the total charge is proportional to the lump's size. And because charge is conserved, the lump can't decay into smaller pieces or individual particles without violating conservation. The lump is stable. It has a definite size determined by the balance between attractive forces, the field's potential energy favoring clumping, and repulsive forces, gradient energy favoring spreading. It has a definite mass, typically enormous, potentially billions or trillions of tons. And crucially, it interacts with ordinary matter primarily through gravity. It doesn't emit light. It doesn't absorb light. It's invisible except for its gravitational influence. This makes cue balls a candidate for dark matter. Dark matter is one of the great mysteries of modern cosmology. We know it exists because we see its effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than their stars and gas account for. Gravitational lensing reveals mass where there's no light. Something is there about 5 times as much something as all the ordinary matter stars, gas planets, you, me combined. But we can't see it. We don't know what it is.
For decades, the leading hypothesis has been weakly interacting massive particles, WIMPs. Hypothetical particles left over from the Big Bang interacting only through gravity and the weak nuclear force pervading the galaxy in a diffuse halo. Experiments have been searching for WIMPs for years. Deep underground detectors, particle colliders, satellite observations. No definitive detection. Cue balls offer an alternative. If dark matter is made of cue balls, macroscopic objects, rather than microscopic particles, they would be incredibly difficult to detect directly. They're not tiny particles you can catch in a detector. They're big, heavy, and they pass through ordinary matter almost without noticing. But occasionally, one might interact. One might get captured by a star, sinking to the core and slowly consuming matter, or one might pass through our solar system. And if it had accreted a mantle of ordinary matter during its billions of years, wandering the galaxy, ice and dust swept up from the interstellar medium, that mantle might start to glow when heated by a star. It would look to us like a comet. This is the scenario the anonymous 4chan post describes. And it's not crazy. It's exotic, yes, unproven absolutely, but it's grounded in real theoretical physics. Let's see how it explains 3I Atlas. The mass problem, a cue ball core would be incredibly dense. 33 billion tons in a 3-kilometer sphere corresponds to a density around 1.5 gcm3 within the range predicted for certain cue ball models. The core is exotic matter, not atoms, not nuclei, but a coherent lump of field energy. Around this core, over billions of years, normal matter accretes.
Hydrogen, helium, water, carbon dioxide, dust, the stuff floating in interstellar clouds. Gradually, the cue ball acquires a mantle of ice and rock, becoming a cosmic snowball with a strange heart. The outgassing without recoil. This is where the cue ball hypothesis shines. If the core has an internal energy source field, energy slowly decaying, converting exotic matter into standard model particles, it creates heat. Not a lot, maybe 73 megawatts, as the 4chan post suggests, but constant. This heat warms the mantle from the inside. Ice sublimates, gas escapes. But here's the key: if the decay is spherically symmetric, if the cue ball is converting field energy uniformly in all directions, then the outgassing is isotropic. Gas leaves the surface in all directions equally. The momentum in each direction is balanced by momentum in the opposite direction. Net thrust 0. The object doesn't recoil because the forces cancel. This explains the A3/0 anomaly perfectly. It's not that outgassing is arranged with precision to cancel vertical forces. It's that there's no asymmetry to begin with. The outgassing is fundamentally symmetric because the energy source is internal and uniform. The thermal indifference, the 15 gigawatts from the sun, trivial. The cue ball has been outputting at 73 megawatts for billions of years. It doesn't care about solar heating. The mantle's temperature is determined by the balance between the internal heat source and radiation to space. Solar input is a small perturbation that affects the outer layers but doesn't change the fundamental thermal state. This explains why 3I Atlas isn't boiling off more water. The sun's heat reaches the surface, but the interior temperature is controlled by the core. The object is thermally autonomous. The chemistry, a cue ball decay, is a particle physics event. Exotic field states convert into quarks, leptons, photons, the ordinary particles of the standard model. But the ratios and types of particles depend on the specific decay pathways which are governed by the field's properties and the symmetries involved. You're not getting ordinary stellar nucleosynthesis, which produces elements in solar abundances. You're getting a different process that might favor certain elements or isotopes. The mantle surrounding the cue ball has been stewing for billions of years in a bath of exotic particle decay products. Perhaps nickel is produced preferentially. Perhaps iron is transmuted or locked into unusual compounds. Perhaps the low-temperature, low-pressure environment inside the mantle creates organometallic species like nickel tetracarbonyl through pathways that don't exist in normal astrophysical settings. The chemistry isn't accidental. It's the exhaust of an ancient engine. The trajectory. If cue balls are a significant component of dark matter, the galaxy is full of them. Billions. Trillions. They're not rare, they're ubiquitous. Most pass through the solar system undetected because they don't scatter light. We only see the ones that happen to have accreted mantles and pass close enough to the sun for those mantles to sublimate. The fact that we found 3I Atlas quickly isn't surprising in this scenario. It's expected. There should be roughly one large cue ball per year passing through the inner solar system based on dark matter density calculations. The Vera Rubin Observatory, with its improved sensitivity, catches them. The trajectory isn't special. The ecliptic alignment is coincidence. With so many objects passing through, some will be aligned. The planetary encounter timing is similarly unremarkable when you're sampling from a large population. The statistical anomalies evaporate, finding a massive object quickly expected, unusual chemistry expected, thermal regulation expected. The cue ball hypothesis turns the anomalies from problems into predictions, but it's testable. The 4chan post makes two specific predictions. First, watch 3I Atlas as it recedes from the sun. A normal comet's activity is solar-driven. As it moves farther away and cools, the sublimation rate drops. Brightness fades according to well-understood thermal models. If 3I Atlas is a cue ball, its activity isn't solar-driven, it's driven by the internal decay. The 73-megawatt engine doesn't care how far from the sun you are. The outgassing rate and brightness should remain high, even as the object moves into the outer solar system, violating every passive thermal model. This is falsifiable. We contest it. By mid-2026, 3I Atlas will be beyond Jupiter. If it's still bright and active at levels inconsistent with solar heating, the natural comet hypothesis fails. Second point, a gamma-ray telescope at it. Cue-ball decay produces high-energy particles.
Some fraction of those particles will interact with the mantle, but some will escape as gamma rays photons with energies in the MeV to GeV range. 73 megawatts isn't a huge luminosity. It's about 1/1,000,000th the sun's output. But at gamma-ray energies, even small fluxes are detectable by sensitive instruments like Fermi or NuSTAR. The signal would be non-thermal, not a blackbody spectrum, but a characteristic distribution from particle decay. It wouldn't correlate with solar distance or solar activity. It would be steady, constant, the heartbeat of the machine. If detected, this would be extraordinary evidence. Not proof you'd need to rule out other gamma-ray sources, but strong evidence that something fundamentally non-standard is happening. As far as I know, no gamma-ray telescope has observed 3II Atlas yet. Telescope time is precious. Proposals require justification.
Convincing an allocation committee to spend time on what sounds like a fringe hypothesis is difficult, especially when the object is faint and the expected signal is weak. But if the cue-ball hypothesis is correct, this would be the discovery of the century: direct detection of macroscopic dark matter, confirmation that dark matter has structure, proof that supersymmetric theories predict real objects that exist in nature. It would rewrite cosmology. Galaxy formation models would need revision to account for macroscopic dark matter objects, not just diffuse particle halos. Our understanding of the early universe and phase transitions would gain experimental grounding. Particle physics would have a new frontier to explore, and it would pose a threat. If cue balls are common and massive, they're an impact hazard. A 33 billion ton object moving at 60 kilometers per second carries kinetic energy equivalent to tens of thousands of megatons. An impact would be an extinction-level event, and we wouldn't see it coming, because cue balls are dark until they're close enough to the sun for their mantles to sublimate. By then, if the trajectory is wrong, there's no time to respond, no way to deflect it. You'd have weeks at most. This is not fear-mongering. This is risk assessment. If the cue ball population is real, and dense, impacts are statistically likely over geological timescales. Perhaps some of Earth's mass extinctions events, without obvious impact craters or asteroid signatures, were cue ball collisions. But let's be clear about the status of this hypothesis. It's speculative. Cue balls are predicted by theories that are themselves unconfirmed. Supersymmetry hasn't been detected at particle colliders. No direct observation of cue balls exists. The entire framework is mathematically consistent, but empirically unproven. We're proposing that 3I Atlas is an example of a phenomenon that's never been confirmed to exist, explained by physics, that's elegant but hypothetical. Why take it seriously? Because the predictions are testable, because it explains the anomalies coherently, and because extraordinary claims backed by testable predictions are exactly what science should pursue rather than dismiss out of hand. December will tell us if the debris cloud exists. 2026 will tell us if activity remains high in the outer system. Gamma-ray observations, if conducted, will tell us if there's a non-thermal signature. The cue ball hypothesis will stand or fall on data, not on how comfortable we are with its implications. And if it stands, if the tests confirm it, then we've discovered that the universe is stranger than we imagined. And the dark matter we've been seeking for 90 years has been passing through our solar system all along, occasionally lighting up like cosmic fireflies when it strays too close to the sun. There's a story from ancient times, possibly fiction, possibly based on real events during the Bronze Age collapse, about a city under siege. Troy had held out for 10 years against Greek invaders. Its walls were strong. Its defenders were skilled. Conventional assault had failed. So the Greeks tried something else. They built a massive wooden horse, filled it with soldiers, and left it outside the city gates as an apparent offering to the gods. Then they sailed away, pretending to abandon the siege. The Trojans, seeing the Greeks gone and finding this mysterious gift, debated. Some argued it was a trick. Others saw it as a trophy proof of victory. Eventually, despite warnings, they brought the horse inside the walls. That night, soldiers emerged from the horse's hollow belly, opened the gates, and let the Greek army in. Troy fell. The city burned. The story endures because it captures something profound about human nature. We judge threats by appearance. Something that looks familiar is assumed safe. We don't check inside. We don't verify. And sometimes that trust is exploited. Dr. Avi Loeb invokes this metaphor when discussing 3I Atlas. He calls it a potential Trojan horse, an object with the external appearance of a natural comet, complete with ice and outgassing and spectral signatures we expect, but potentially carrying something else inside. This is the artificial hypothesis, and before dismissing it as wild speculation, understand that Loeb isn't saying 3I Atlas is definitely artificial. He's saying the data doesn't rule it out, and that responsible science means considering all hypotheses consistent with observation, then testing them. So let's consider it carefully, not as believers, not as skeptics, but as researchers examining whether the artificial origin hypothesis organizes the data coherently and makes testable predictions. Start with the trajectory. If you were designing an interstellar probe to survey our solar system, how would you approach? You'd want a trajectory that encounters multiple planets. You'd choose retrograde motion in the ecliptic plane because it maximizes relative velocity and ensures you pass by planetary orbits quickly rather than slowly catching up. You'd time your perihelion for when Earth, the most technologically advanced planet, the most likely to detect and track, you cannot observe. 3I Atlas's trajectory accomplishes exactly this. Mars' close approach in early October, when Mars orbiters could observe. Perihelion on October 29th during solar conjunction from Earth. Venus pass in November. Jupiter encounter in March 2026. Is this proof of design? Number geometry is geometry, and any retrograde ecliptic orbit will encounter planets. The timing is low probability, 0.005%, but not impossible. Chance can produce patterns that look intentional, but it's consistent. That's all. We're establishing consistency, not proof. Now consider engineering. If you're sending a probe across interstellar distances, journeys lasting millions or billions of years, how do you protect it? Metal hulls are heavy and vulnerable. Radiation damages electronics. Micrometeorite impacts erode surfaces. Temperature swings stress materials. Over cosmic timescales, even the most robust engineering degrades. A better approach: let the probe acquire its own shielding during the journey. As it travels through the interstellar medium, thin gas and dust, mostly hydrogen with traces of heavier elements, it sweeps up material. Hydrogen atoms stick to cold surfaces. Water molecules, carbon dioxide dust grains all accrete gradually. Over millions of years, you build a thick protective layer. This layer provides radiation shielding, micrometeorite protection, thermal insulation. And crucially, when the probe approaches a star, this icy mantle sublimates. The probe looks like a comet. Natural camouflage. You blend in. You don't trigger alarms. By the time anyone realizes you might not be natural, you've completed your observations and you're leaving. This concept isn't science fiction. It was discussed seriously in the 1960s by researchers thinking about long-duration interstellar missions. You don't carry all your shielding with you, you grow it en route. 3I Atlas fits this profile. It has an icy mantle that's outgassing. It has the chemical signatures of a comet. But underneath the anomalies suggests something else: mass too high, thermal behavior, too regulated chemistry, too strange. The nickel becomes interesting in this context. If you're building a probe and you need structural materials, what do you use? Steel is obvious, strong, durable, well understood. But steel is mostly iron. If your probe's structure is nickel steel or pure nickel, and if the surface is ablating eroded by impacts and radiation over billions of years, then when the icy mantle sublimates near a star, you'd see nickel vapor being released, not from the ice, but from the underlying structure. Nickel tetracarbonyl is how we refine nickel to extreme purity on Earth. It's a volatile compound easy to handle if you have the right equipment. If an ancient probe used nickel-based alloys, and if those alloys are reacting with carbon monoxide in the coma, you'd get exactly the chemistry we're observing. Strong nickel emission, no iron, and a volatile compound mediating the release. This is highly speculative, but it's internally consistent. The energy budget makes sense in this framework. At perihelion 3I Atlas was absorbing 15 gigawatts from the sun. A passive body would heat up until it reaches thermal equilibrium. Absorbed power equals radiated power. But if the probe has an internal power system, perhaps a nuclear decay source, or a cue-ball core, or some energy storage mechanism, we don't understand it can manage heat actively, pump excess energy from the sunlit side to the dark side, radiate it away in the infrared at wavelengths we haven't carefully measured, keep the surface temperature locked in a specific range. Active thermal management would explain why water isn't dominating the outgassing despite intense solar heating. The surface temperature is regulated below water's sublimation threshold. Only the more volatile carbon dioxide and carbon monoxide are released in significant quantities. The dust properties' extreme negative polarization align with engineered materials. Aerogel nanofoam structured composites designed for thermal insulation or radiation shielding have complex optical properties. When shed as dust, they'd produce polarization signatures different from natural aggregates. And the acceleration pattern, the perfect in-plane thrust with A3 Cassandra EO, becomes not an anomaly, but a signature. A probe with attitude control wouldn't thrust randomly. It would thrust deliberately, maintaining its orientation and orbital plane. If it needed to adjust velocity for some reason, perhaps to align a sensor or to fine-tune its Jupiter encounter or to correct for perturbations, it would fire thrusters with precision. Natural comets thrust chaotically. Designed systems thrust with control. But if 3I Atlas is artificial, what's its purpose? What's it doing? The optimistic answer: exploring. Gathering data, mapping the solar system, taking measurements of planetary atmospheres, magnetic fields, radiation environments, recording everything with sensors we can't see, storing data for transmission back to wherever it came from. This is what our probes do. Voyager, New Horizons, Cassini, they're scouts, explorers, gathering knowledge. If another civilization has the capability to send probes across interstellar distances, they might be doing the same. Curiosity, science, understanding. If this is the case, 3I Atlas is not a threat. It's an opportunity, a chance to learn about another technological civilization, to see what they considered worth exploring, to understand their capabilities. But there's a darker possibility, the dark forest hypothesis. This is an idea from science fiction Liu Cixin's novel, The Three-Body Problem, but it's been discussed seriously by researchers thinking about the Fermi paradox. Why haven't we detected other civilizations, despite the galaxy being old enough for them to have arisen many times? One answer: civilizations hide because the galaxy is dangerous. If you reveal your presence by broadcasting radio signals, launching conspicuous probes, making yourself visible, you risk attracting attention from someone more advanced who might view you as a threat or a resource to be exploited. In this scenario, the galaxy is full of civilizations, but they're all silent, staying dark, observing, but not revealing themselves. And they send probes to assess new arrivals. When a planet develops technology, radionuclear weapons spaceflight, it becomes visible, and probes come to evaluate. Is this civilization dangerous? Should it be left alone, or should it be neutralized before it becomes a problem? If 3I Atlas is a reconnaissance probe sent under dark forest assumptions, its mission is to observe Earth and determine our threat level. The perihelion timing during solar conjunction makes sense, minimize detection risk, while maximizing observation opportunities. The planetary encounters assess the local environment, checking for bases or activity on Mars, Venus, moons. What happens after reconnaissance? If we're deemed harmless, perhaps nothing. The probe leaves reports back, and we're cataloged as a primitive species not worth concern. But if we're deemed threatening, if our technology is advancing too quickly, if we're too aggressive, if we represent future competition, then maybe a follow-up mission comes. Something larger, something not designed to observe, but to act. This is paranoid speculation. It's the kind of thinking that makes mainstream scientists uncomfortable because it verges into science fiction, and science shouldn't be fiction. But here's the thing. The dark forest hypothesis is internally consistent. It explains the Fermi paradox. It predicts exactly what we observe, a silent galaxy with no obvious signs of other civilizations, but the occasional unexplained object passing through that might be surveillance. If you're taking the artificial hypothesis seriously at all, you have to consider intent. And intent ranges from benign exploration to hostile reconnaissance. The good news, if there is any, is that 3I Atlas is leaving. It's not parking in orbit around Earth. It's not setting up a base on Mars. It's on a hyperbolic trajectory that takes it out of the solar system and back into the void. Whatever its mission was, it's ending, unless it release subprobes. Small satellites left behind in strategic locations, drifting in unusual orbits, too small to detect, with current surveys quietly observing and transmitting data back to the mothership. This is the nightmare scenario, and there's zero evidence for it. But if 3I Atlas is artificial, it's a logical possibility. You send a large probe that attracts attention, while small, unobtrusive satellites do the real work. The big probe distracts. The small ones observe. How would we detect subprobes? Dedicated surveys of unusual orbits. Radio monitoring for anomalous transmissions. Infrared searches for objects with thermal signatures inconsistent with natural bodies. We're not doing these searches systematically because we're not treating the artificial hypothesis seriously enough to allocate resources. Dr. Loeb argues we should. Not because the artificial hypothesis is likely it's not by most assessments, but because the consequences, if we're wrong, are severe. If this is a probe and we ignore it, we miss a once-in-civilization opportunity to study extraterrestrial technology. If this is a probe with hostile intent and we ignore it, we leave ourselves vulnerable. The Trojan horse fell because defenders assumed safety. They didn't check inside, they paid the price. Loeb is saying, check inside, use every tool, gamma-ray telescopes, high-resolution imaging, spectroscopy, radio dishes. Look for anything that doesn't fit the natural model. And if we find something, deal with it. Don't assume. Verify. The problem is resources and institutional inertia. Telescope time costs money. Spacecraft missions cost billions and take years to plan. Convincing agencies to spend resources on a low-probability scenario is difficult, but the risk-reward calculation is asymmetric. If 3I Atlas is just a weird comet, we waste some time and learn about exotic chemistry. If it's a probe, we potentially learn things that change human civilization forever. The cost of checking is small. The cost of not checking, if we're wrong, is enormous. So why aren't we checking more aggressively? Partly institutional conservatism, partly scientific caution. Most astronomers believe 3I Atlas is natural and don't want to waste resources chasing low-probability hypotheses. Partly fear of being wrong, fear of looking foolish, fear of being the person who cried alien and got laughed out of the field. But fear is corrosive. It prevents bold inquiry. It makes us conservative when we should be curious. The artificial hypothesis is speculative. It might be wrong, probably is wrong, but it's testable. The debris cloud test applies here too. If the cloud is there, the natural explanation is simpler. If absent alternatives, including artificial origins, remain viable. And there are other tests. Does activity remain high far from the sun? Is there a gamma-ray signature? Are there anomalies in the orbit that suggest course corrections? We won't know unless we look. The Trojan horse sits outside our gates. It looks like a gift, a natural comet, a piece of interstellar debris, nothing to worry about. We can bring it inside metaphorically, assume it's safe, and move on with our lives. Or we can check first, verify, make sure we're not missing something that matters. The defenders of Troy didn't check. History remembers their mistake. We have a chance to do better. There's a peculiar quality to institutional silence. It's not the absence of sound, but the presence of vacuum, a space where explanation should exist, but doesn't. When data goes missing, when releases are delayed without justification, the vacuum fills with speculation. And speculation unchecked breeds mistrust. 1 month ago, on October 2nd and 3rd, 2025, the HiRISE camera aboard NASA's Mars Reconnaissance Orbiter photographed 3I Atlas as it passed within 30 million kilometers of Mars. HiRISE, the high-resolution imaging science experiment, is the most powerful camera ever sent to another planet. Its angular resolution is 1 microradian, which translates to about 30 centimeters per pixel, when imaging the Martian surface from orbit. From 30 million kilometers away, that resolution means each pixel captures roughly 30 kilometers of 3I Atlas. Not enough to see the nucleus directly. If it's only 5 kilometers across, it would appear as a fraction of a pixel. But more than enough to measure the coma's brightness distribution, to detect asymmetries, to see structure in the gas and dust envelope, to characterize the overall brightness and compare it to earlier observations. These images should be the best close-up views of 3I Atlas we have before December's Earth flyby. Better than anything Hubble captured in July from 570 million kilometers, 3 times better resolution, 20 times closer. But as of early November, the images haven't been released. No publication, no press release, no data dump to the planetary data system where NASA's archived observations are supposed to become publicly available. Just silence. Dr. Loeb requested the data directly from Professor Alfred McEwen, the principal investigator of the HiRISE camera team at the University of Arizona. No response. Congresswoman Anna Paulina Luna submitted an official letter to NASA asking for the image's release, citing scientific importance and public interest. No response from NASA, no timeline provided. The official explanation, to the extent there is one, invokes the government shutdown. In early October, the U.S. federal government entered a partial shutdown due to budget negotiations. NASA employees were furloughed. Operations were disrupted. Data processing pipelines that normally run automatically were paused. This is plausible. Government shutdowns create chaos. Timelines slip. Work that should take days takes weeks. It's happened before, but here's the problem. The shutdown ended weeks ago. Operations resumed, and other Mars missions released their data. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter both observed 3I Atlas during its Mars flyby and released images within days. Lower resolution than HiRISE, yes, but publicly available with minimal delay. Why is HiRISE different? One possibility: the data is still being processed. Raw spacecraft images aren't immediately usable. They need calibration corrections for instrumental artifacts, flat fielding to account for sensor variations, geometric corrections, conversion from digital counts to meaningful physical units like radiance or reflectance. This takes time.
And HiRISE is designed for imaging the Martian surface, not faint comets millions of kilometers away. Processing an image of 3I Atlas might require custom procedures, different exposure times, different pointing strategies, different calibration approaches that the team is still working through. If this is the reason, it's defensible, but it requires communication. Put out a statement, "We have the data. We're processing it. It will be ready in X weeks." That would diffuse speculation. Instead, silence. Another possibility, the images show something unexpected, and the team wants to be absolutely certain before releasing anything. If the brightness is way off from predictions, if there's an unusual feature in the coma, if anything looks inconsistent with a standard comet, then caution is understandable. You don't want to release preliminary results that might be misinterpreted or that might turn out to be artifacts. Scientific caution is good. Peer review is good.
But there's a line between caution and obstruction. When data is collected by publicly funded missions, spacecraft paid for by taxpayers, transparency should be the default, not the exception. Or maybe it's purely bureaucratic. NASA has procedures for data releases, formal review processes, approvals from multiple levels of management documentation requirements. These procedures exist for good reasons, ensuring data quality, avoiding premature claims, but they're slow. Combine slow bureaucracy with a government shutdown and a controversial target, and delays compound. Maybe the images are sitting on a server somewhere fully processed, waiting for someone to sign off. And that person is either too busy, too cautious, or too uninterested to prioritize it. Any of these explanations could be true. But the result is the same. 1 month after observation, we don't have the data. And the longer the delay, the more suspicious it looks, regardless of the actual reason. Enter Kim Kardashian. On November 2nd, 2025, Kardashian tweeted to her 400 million followers, "Wait, what is the T on 3i Atlas?" The tweet went viral, millions of impressions within hours. Major news outlets picked it up. Suddenly, an obscure interstellar comet discussed mainly in academic circles was headline news. NASA Acting Administrator Shaw Duffy responded the same day. Great question. NASA's observations show that this is the third interstellar comet to pass through our solar system. No aliens, no threat to life here on Earth. Short. Dismissive, reassuring in a way that raises more questions than it answers. Because here's the thing, Kardashian asking about 3i Atlas isn't random celebrity nonsense. She has a massive platform. When she asks a question, people pay attention, and the question she's asking, what's going on with this object, is the right question. Why is it strange? Why are scientists arguing about it? Why does it feel like we're not getting straight answers, Doctor? Loeb responded to the exchange by saying he would love to bring Kardashian up to date on all the anomalies. He meant it sincerely, because at this point, public attention is one of the few mechanisms that can push institutions toward transparency. If millions of people are asking why the high-rise images haven't been released, it becomes harder to ignore. The question moves from niche academic circles to mainstream discourse. Elected officials take notice. Agencies feel pressure to respond. This shouldn't be necessary. Data releases should be automatic, timely, transparent. But when they're not, public pressure becomes a forcing function. What would the high-rise images show? We don't know, that's why we need to see them. But we can make educated guesses. First, brightness measurements. The total brightness of the coma gives estimates of how much light is being scattered by gas and dust. Compare this to Hubble's July observations and ground-based measurements, and you can track how brightness has evolved. If it increased significantly between July and October, that indicates ramping activity as the comet approached perihelion. If it stayed constant, that's unusual. Most comets brighten closer to the sun. Second, morphology. The shape and structure of the coma reveal outgassing patterns. Is it round and symmetric or elongated with jets? Hubble saw a faint anti-tail pointing toward the sun. Does HiRISE see the same feature? Is it more pronounced? Are there other structures? Fans, streamers, shells that weren't visible in lower resolution images, third size constraints. If the nucleus is large enough and the coma not too diffuse, HiRISE might resolve the central concentration of light corresponding to the nucleus plus inner coma. This would tighten estimates of the solid body size, which currently range from 5 to 46 kilometers, depending on assumptions about how reflective the surface is. Fourth, color information. HiRISE has multiple filters, not as many as Hubble, but enough for crude color measurements. If there's any truth to the controversial reports of unusual color near perihelion HiRISE, data might confirm or refute it. Any of these measurements would be valuable. All of them together would be invaluable. They'd inform observation planning for December's Earth flyby. They'd help constrain models of the object's activity and composition, but we don't have them. And we don't have an explanation for why we don't have them. This erodes trust. Not just in NASA, an agency with decades of transparent operations and public data releases, but in the process. When people see data being withheld without justification, they assume the worst. Maybe the images show something embarrassing. Maybe they contradict earlier statements. Maybe they're too ambiguous to interpret confidently, and releasing them would spark controversy. Or maybe it's just bureaucratic incompetence. Hanlon's razor never attribute to malice what can be adequately explained by stupidity. But stupidity or malice, the result is the same. Trust erodes, speculation grows, and the story becomes not just about the object, but about the response to the object. There's a lesson here about transparency. When you're dealing with something that captures public attention, a mysterious interstellar visitor, an object that might challenge our understanding, transparency isn't optional. It's essential. People are smart. They can handle ambiguity. They can handle uncertainty. What they can't handle is silence, because silence implies hiding something even when you're not. NASA, if you're listening, release the HiRISE images. Do it now. Do it with a clear explanation of what they show and what they don't show. Do it before December while the data is still useful for planning observations. And do it because it's the right thing to do. The images were taken by a publicly funded mission. The data belongs to the public. Transparency is not a favor, it's an obligation. The T on 3i Atlas to answer Kim Kardashian's question is that we don't have all the data we should have. And until we do, the questions will keep coming from scientists, from journalists, from members of Congress, from reality TV stars with 400 million followers. Because at the end of the day, this isn't about celebrity gossip or academic politics. This is about understanding an object that might be ordinary or might be extraordinary, and we can't make that determination without seeing all the evidence. December 19th is 6 weeks away. By then, the HiRISE images will be old news, superseded by fresh observations from Earth-based telescopes. If released before December, they inform the observation campaign. If released after, they're a footnote. The clock is ticking. The window for relevance is closing. And every day of silence makes the eventual release less impactful and more suspect. Someone at NASA click the button, release the data, let science proceed. There's an elegant simplicity to thermodynamics. Energy flows from hot to cold. Systems trend toward equilibrium. You can't create or destroy energy, only transform it. And when you transform it, some always becomes waste heat, the universe's entropy tax. These aren't suggestions, they're laws. Not in the legal sense, but in the physical sense, they govern how reality operates at the most fundamental level. So when an object appears to violate thermodynamics, or at least behave in ways that strain standard thermal models, we pay attention. Let's do some calculations. At perihelion, 3i Atlas was 1.36 astronomical units from the Sun. 1 AU is the Earth-Sun distance, about 150 million kilometers at 1.
36. AU sunlight intensity is reduced by the inverse square law, 1.36, 2.54 times the intensity at Earth. At Earth solar irradiance, the power per unit area is about 1,361 watts per square meter. At 1.36 AU, it's roughly 770 watts per square meter. Now consider a spherical object 5 kilometers in diameter. The cross-sectional area presented to the Sun is PR2, where r is the radius. For a 5-kilometer sphere, r hadras 2,500 meters, so the cross-sectional area is px to 502, 19.6 million square meters. Multiply area by irradiance, 19.6 million m2x 770 wm2, 15 gigawatts. 15 billion watts of solar energy absorbed at perihelion. For comparison, that's roughly the electrical generating capacity of New York City. What happens to this energy? In a normal passive body, it heats the surface. The temperature rises until the object reaches thermal equilibrium, the point where energy radiated away, as infrared light equals energy absorbed from sunlight.
You can calculate the equilibrium temperature using the Stefan-Boltzmann law. The power radiated by a surface is St4a, where As is the Stefan-Boltzmann constant, T is temperature in Kelvin, and A is the surface area. Set absorbed power equal to radiated power and solve for T. For a simple calculation, assuming the object is a perfect black body, it absorbs all light and radiates efficiently, rotating fast enough that heat distributes uniformly, and accounting for the fact that it absorbs over cross-sectional area but radiates over total surface area, the equilibrium temperature works out to around 270 Kelvin, just below the freezing point of water. But comets aren't perfect black bodies, and they don't distribute heat uniformly. The subsolar point, the spot where the sun is directly overhead, gets much hotter than the average. Depending on rotation rate, thermal conductivity, and surface properties, local temperatures at perihelion can easily reach 300–350 Kelvin or higher. At these temperatures, water ice sublimates rapidly, not gently explosively. The vapor pressure of ice at 300 K is high enough to drive vigorous outgassing. A comet this close to the sun should be boiling off water, creating a massive coma dominated by H2O and its photodissociation products like OH and H. But 3I Atlas's outgassing is only 4% water. The rest is carbon dioxide, carbon monoxide, and other volatiles. The thermal observations, admittedly preliminary and difficult to interpret, suggest the surface is cooler than expected for passive heating. Where is the energy going? One possibility into sublimation. When ice transitions from solid to gas, it absorbs latent heat energy required to break molecular bonds and free molecules from the solid lattice. This is why sweating cools you. The water evaporating from your skin carries away heat. If 3I Atlas is sublimating 150 kilograms per second, and if that material is carbon dioxide with a latent heat of sublimation around 600 kilojoules per kilogram, then sublimation is consuming 150 kilojoules x 600,000 J kilo 90 megawatts. That's significant, but nowhere near 15 gigawatts. You're accounting for less than 1% of the absorbed solar energy through sublimation. The rest has to go somewhere. Radiation. If the surface is cooler than expected, it's radiating less than it should. That doesn't help. It makes the energy budget worse, not better. Thermal conduction into the interior, if the object is large and has low thermal conductivity. As ices generally do, heat doesn't penetrate quickly. The surface heats up and radiates while the interior stays cold. This is normal for comets, but it doesn't explain why the surface itself appears cooler than expected, unless there's active heat transport. Some mechanism moving energy from the sunlit side to the dark side, or from the surface to the interior, maintaining temperature gradients that passive conduction wouldn't produce. This requires a system. Natural bodies don't have thermal management systems. They heat and cool according to how much energy they absorb and radiate. Temperature is the result, not something controlled. But if 3I Atlas has an internal energy source, if it's outputting heat from within, then the thermal picture changes completely. The sun's 15 gigawatts become a perturbation on top of the internal output. The object's temperature is determined by the internal source, not by solar heating. If the internal source is 73 megawatts, as the cue ball hypothesis suggests, then the sun's 15 gigawatts is still dominant. But if the interior has been warm for billions of years, the thermal structure of the mantle is different. Heat flows outward from the core. The mantle maintains a temperature profile determined by that outward flow. Solar heating affects the outermost layers, maybe the top few meters, but doesn't penetrate deeply because the interior is already warm. In this scenario, the low water abundance makes sense. Water sublimates at lower temperatures than carbon dioxide if pressures are low. But in the interior of a thick ice mantle being warmed from below, you can create conditions where carbon dioxide is released preferentially. Depth, pressure, temperature all matter. Complex thermal structures can produce counterintuitive chemistry. This is speculative. We're invoking an internal heat source we haven't confirmed exists to explain thermal behavior we haven't measured carefully, but it fits the pattern. 3I Atlas behaves as if it's thermally autonomous, as if the sun is an external annoyance rather than the primary energy source. Compare this to normal comets. When Rosetta orbited Comet 67P, Churyumov-Gerasimenko instruments measured surface temperatures carefully as the comet approached and receded from the sun. Temperatures followed predictable curves. Activity correlated with solar distance. Everything matched passive thermal models with minor corrections for rotation and topography. If 3I Atlas behaves the same way, if activity declines as it moves away from the sun according to standard curves, then the thermal anomaly was just preliminary data misinterpreted and the natural explanation holds. But if activity stays high far from the sun, defying passive thermal predictions, then we need a new explanation. And internal energy sources move from speculation to necessity. December and the months after will tell us. The IAWN campaign tracks 3I Atlas through January 2026. Observations will continue as long as the object is bright enough. By mid-2026, when it's beyond Jupiter and receiving less than 4% of the sunlight it got at perihelion, its activity should have dropped dramatically if it's solar-driven. If it hasn't, if 3I Atlas is still bright and active at levels inconsistent with solar heating, then thermodynamics hasn't been violated. But our assumptions about what's driving the activity have been. There's a philosophical point here. The laws of thermodynamics are inviolable, but our models of how those laws apply to specific situations are fallible. When observation conflicts with model, it's not the laws that are wrong, it's the model's assumptions. Maybe 3I Atlas has an internal energy source. Maybe it has chemistry we don't understand that stores and releases energy in unexpected ways. Maybe it has properties high thermal conductivity, unusual surface coatings, asymmetric outgassing that carries heat away, preferentially that our models haven't accounted for. We don't know.
But we're about to learn, and every anomaly, every time reality surprises us, is an opportunity to refine our understanding. Thermodynamics will be fine. Our egos might take a hit when we realize how much we didn't know. But that's how science works. The universe is under no obligation to make sense to us on first inspection. Mark your calendar. December 19th, 2025. That's the day 3I Atlas makes its closest approach to Earth at 267 million kilometers, about 1.78 astronomical units, roughly the distance from the Sun to Mars. It's not close in human terms, not even close in solar system terms, but it's close enough for hundreds of professional telescopes to observe it simultaneously. Close enough for Hubble and James Webb to take high-resolution spectra, close enough for large ground-based observatories to measure the coma's brightness distribution and search for extended emission, close enough to test the debris cloud hypothesis. Let's review what we're looking for. During perihelion, 3I Atlas experienced non-gravitational acceleration that required, according to standard outgassing models, the ejection of 3 to 5 billion tons of gas and dust. That's 10 to 15% of the object's total mass, assuming a mass around 33 billion tons.
When gas sublimates from a comet nucleus, it doesn't vanish. It expands outward at the thermal velocity of the molecules a few hundred meters per second for carbon dioxide and water at the temperatures expected in the coma. The gas carries dust with it. Together, they form a diffuse cloud around the nucleus. By December 19th, 2 months after perihelion, that expelled material will have traveled roughly 5 million kilometers from the nucleus. It will have spread into a giant tenuous cloud still centered on the object, but vastly larger than the nucleus itself. The cloud will be faint. Gas density drops as 1/distance cubed as the material expands, so by the time it's spread over 5 million kilometers, it's incredibly thin. But it's not invisible. The gas molecules scatter sunlight, especially in specific spectral lines, carbon dioxide bands in the infrared carbon monoxide lines, in ultraviolet and visible cyanide emission in blue-green. And crucially, the total amount of gas is huge. Even spread thin billions of tons of material scattering sunlight should produce a detectable signal. This is what we're looking for: extended emission around 3I Atlas, spatially resolved, meaning we can measure how far from the nucleus the glow extends with brightness and spectral lines consistent with the expected amount of gas. Multiple telescopes will be involved: Hubble Space Telescope, ultraviolet and optical imaging, and spectroscopy. Hubble has observed 3I Atlas before, so comparison between July and December will show how the coma has evolved.
Spatial resolution is excellent for detecting extended structures. James Webb Space Telescope, infrared imaging and spectroscopy, sensitive to carbon dioxide and carbon monoxide. Webb's detectors can measure very faint emission, ideal for detecting a tenuous extended cloud. Ground-based observatories. Keck, the Very Large Telescope VLT in Chile, Gemini Subaru. All large telescopes with adaptive optics and sensitive spectrographs. These can take repeated observations over multiple nights, building up signal and measuring variability. ALMA Atacama, large millimeter. Array radio observations at millimeter wavelengths, directly detecting carbon monoxide molecules through their rotational emission lines. ALMA is less affected by dust scattering and can map gas distribution with high sensitivity. Each telescope sees different aspects of the cloud. Optical sees sunlight scattered by dust and emission from molecules like CN and C2. Infrared sees carbon dioxide and water.
Millimeter wavelengths see carbon monoxide. Together, they provide a complete picture. If the debris cloud is there, all these instruments will detect it. The signal will be consistent across wavelengths. The spatial extent, how far the emission reaches from the nucleus, will match the expected expansion from material ejected at perihelion. The total brightness and inferred mass will align with the billions of tons required to explain the acceleration. If that happens, the natural comet hypothesis is confirmed. 3I Atlas accelerated because of outgassing just like other comets, and the anomalies, while unusual, are explicable within the framework of exotic but natural chemistry and formation conditions. The mystery doesn't entirely disappear. We'd still want to understand the nickel chemistry, the thermal behavior, the perfect in-plane acceleration. But the most straightforward test: did the comet eject the mass it should have passes? And that makes the natural explanation simpler. But what if the cloud isn't there? What if Hubble Webb and the ground-based telescopes see only a compact coma emission confined to the immediate vicinity of the nucleus, with no extended halo stretching millions of kilometers? What if the total mass of gas in the coma is orders of magnitude smaller than the billions of tons required? Then the outgassing hypothesis fails. You can't accelerate an object through the rocket effect without ejecting reaction mass. Conservation of momentum is non-negotiable. If the mass wasn't ejected, something else caused the acceleration: internal propulsion, directed energy, a process we don't have a name for. At that point, the natural comet explanation becomes untenable. You can stretch it with ad hoc assumptions. Maybe the gas was ejected but somehow became invisible. Maybe it was ionized and swept away by solar wind faster than expected. Maybe our mass calculations are wrong by an order of magnitude, but each rescue gets more contrived. Occam's razor would then favor alternatives, either the cue ball hypothesis with its internal energy source, producing symmetric outgassing that doesn't create net thrust, or the artificial hypothesis with controlled thrusters. Both are exotic. Both require accepting that our understanding of what's possible is incomplete. But if the data demands it, that's where we go. There's a third possibility, and it's the most likely ambiguity. Science is messy. Real data has uncertainties. Maybe we see a cloud, but it's smaller than expected. Maybe we see extended emission, but interpreting it requires assumptions about gas temperature and density that have large error bars. In that case, the debate continues. Papers get published arguing both sides. Conferences host sessions where researchers present conflicting interpretations. The community gradually converges on a consensus or doesn't, and the object becomes one of those perennial mysteries with competing camps. This happens. Not every question gets a clean answer. Sometimes nature gives us ambiguous signals, and we do our best to interpret them with the tools we have. But December 19th will constrain the possibilities. Even if we don't get a definitive answer, we'll narrow the range of plausible explanations. And as more data accumulates through the IAWN campaign, through follow-up observations into 2026, the picture will sharpen. Beyond December, there are other milestones: International Asteroid Warning Network, IAWN campaign. From November 27, 2025 to January 27, 2026, multiple observatories worldwide will coordinate observations, sharing astrometric data to refine the orbit and track non-gravitational acceleration. This provides the highest precision orbital data we've ever collected for an interstellar object. ESA's JUICE spacecraft observations. JUICE en route to Jupiter observed 3I Atlas in late November from a different vantage point than Earth. Data transmission is slow due to distance, so results won't arrive until February 2026, but they'll provide an independent check on the object's brightness and activity. Mars, 2026 encounter. As 3I Atlas passes Jupiter in March, it'll be far enough from the Sun that activity should have declined significantly if solar-driven. Observations during this period test whether the object is still active at levels inconsistent with passive thermal models. By mid-2026, the cumulative evidence will paint a clear picture, or as clear as we're going to get, before the object fades beyond observability. And there's still the gamma-ray test. If someone points Fermi or NuStar at 3I Atlas and integrates for long enough, they might detect the 73 megawatt signature predicted by the cue ball hypothesis. That would be extraordinary evidence, not proof, because you'd need to rule out other gamma-ray sources, but strong support for exotic physics. As far as I know, no gamma-ray observation has been announced. Maybe none has been attempted. Maybe it was attempted and the result was negative, but negative results don't generate press releases. We won't know unless someone publishes. The next 6 weeks are critical. December 19th is the focal point, the moment when the most powerful telescopes humanity has built will turn toward a small, dark object and measure whether it behaves as expected. Either physics proceeds as we understand it, or we learn something new. Either way, the data will be fascinating, and the story, whatever it turns out to be, will have moved from speculation to knowledge. We're 45 days from answers. The countdown is on. There's a question that doesn't get asked often enough in astronomy: how many interstellar objects are passing through our solar system right now that we simply don't see? Before 2017, the answer was, we have no ideas, possibly none, possibly thousands. We had theories about ejection rates from planetary systems and calculations of how many free-floating objects should exist in the galaxy based on planet formation models. But no detections, no data, just mathematical predictions waiting for observational confirmation. Then, Oumuamua appeared, and the answer became at least one, probably many more. Now we have 3 confirmed interstellar visitors in 8 years. That's a detection rate far higher than early models predicted, even accounting for improving survey capabilities. Let's think about what this means. When planetary systems form, there's a lot of jostling. Planetesimals collide, merge, get scattered. Giant planets migrate inward or outward, flinging smaller bodies into chaotic orbits. Some crash into the sun. Some settle into stable orbits, becoming asteroids or Kuiper belt objects.
And some gravitationally kicked by Jupiter or Saturn or equivalent giants in other systems reach escape velocity and leave the system entirely. These ejected objects become interstellar wanderers. They're not bound to any star. They drift through the galaxy at tens of kilometers per second on trajectories that might eventually take them close to another stellar system millions or billions of years later. Over the galaxy's 10-billion-year history, countless objects have been ejected from countless planetary systems. They form a background population, a sea of rocks and ice balls drifting between the stars. Early models based on our understanding of planet formation and ejection rates predicted we'd find maybe 1 interstellar object per year with a next-generation survey telescope like Vera Rubin. That seemed reasonable. Not common, but not vanishingly rare either. But we found 3 objects before Rubin went fully operational.
And the progression is troubling, each one larger and faster than the last. If we're sampling randomly from a population where small objects vastly outnumber large ones, which is how size distributions work for asteroids and comets, we should find many small objects before finding large ones. Instead, we found a giant in our 3rd detection. This could be luck. Statistics allows for unlikely sequences, but it could also mean our models are wrong. Either large objects are more common than we thought, which would require revision of ejection models and planet formation theories, or detection bias is stronger than we realized, favoring large active objects over small inert ones, or we're not sampling randomly at all. If the cue ball hypothesis is correct, we're not detecting interstellar debris. We're detecting a component of dark matter, and dark matter is everywhere. Let's do some calculations. The local dark matter density near the Sun is about 0.3 GeV cm3, which translates to roughly 5 x 10 to 24 grams per cubic centimeter. That's extraordinarily diffuse, far less dense than the best laboratory vacuums, but integrated over the vast volume of the galaxy, it's the dominant form of matter. If cue balls make up a significant fraction of that dark matter, and if a typical cue ball has a mass of 33 billion tons, sun 3 x 1013 kg, then the number density of cue balls is around 1.5 1037 per cubic centimeter, or about 1 cue ball per 1037 cubic centimeters. That sounds sparse, but the solar system is huge. The volume of space within, say, Neptune's orbit 30 AU radius is enormous. And cue balls are moving. They have a velocity dispersion of a few hundred kilometers per second, typical of dark matter halos. The flux of cue balls passing through the solar system depends on density, velocity, and geometry. A rough calculation gives something like 1 to 10 cue balls passing within a few AU of the Sun per year, close enough that if they have ice mantles, those mantles would sublimate and become visible. Finding 3I Atlas within months of improved survey capabilities would not be surprising. It would be expected. And it predicts we'll find more. Vera Rubin, with its sensitivity and sky coverage, should detect interstellar objects at a rate of 1 every few months. If a significant fraction of those show properties similar to 3I Atlas' large, dense, strange chemistry, it supports the cue ball hypothesis. But if most are mundane, small, icy, with normal chemistry, and 3I Atlas is an outlier, then it's either a statistical fluke or something special. The next 5 years of Vera Rubin observations will tell us. By 2030, we'll have dozens of interstellar objects cataloged. We'll know their size distribution, composition, distribution, trajectory distribution. We'll see patterns that are invisible with a sample size of 3. If the artificial hypothesis is correct, the implications are different but equally profound. If 1 in 100 interstellar objects is artificial, a probe from another civilization, and if Vera Rubin detects 10 per year, then we should find another potential probe within a decade. Maybe sooner if our ability to recognize anomalies improves. Multiple detections with similar anomalies would be compelling. One object with weird properties is curiosity. 5 objects all showing nickel without iron, unusual thermal behavior, and controlled trajectories, that's a pattern demanding explanation. But there's another scenario. What if artificial probes are common? What if the galaxy has been explored and surveyed by multiple civilizations over billions of years, and probes are everywhere? This is the Bracewell probe hypothesis, named after radio astronomer Ronald Bracewell, who proposed in 1960 that the most efficient way to explore the galaxy isn't to send radio signals, but to send self-replicating probes. A single civilization launches a few probes. Those probes travel to nearby star systems, build copies of themselves from local materials, and send those copies onward. Exponential growth. Within a few million years, a blink in galactic time, every star system has been visited. The galaxy is thoroughly surveyed not by radio waves, but by physical artifacts, quietly observing, recording, perhaps occasionally transmitting data back to their creators if those creators still exist. If this is real, then the galaxy is ancient and crowded in a way we don't see. Silent watchers everywhere. And 3I Atlas might be one of them, an ancient probe launched billions of years ago, still operating, still functional, passing through our system on a routine patrol. This sounds like science fiction, but it's mathematically consistent. It explains the Fermi paradox. We don't see other civilizations because they're not broadcasting. They're observing quietly, and the galaxy is a library of stored knowledge rather than a cacophony of signals. Detecting such probes requires looking for anomalies, objects that don't quite fit natural models. And that's exactly what we're doing with 3I Atlas. Whether cue balls or probes, the common thread is that the galaxy is more densely populated with interesting objects than we realized. We've been flying blind, seeing only the stars, and assuming the space between is empty. It's not empty. It's full of ejected planetesimals, full of dark matter structures, possibly full of artifacts from civilizations that rose and fell before our sun was born. And we're just beginning to see 3 objects in 8 years, dozens expected in the next decade, hundreds by 2040. The age of interstellar object astronomy is just beginning, and we're poised on the threshold of a new understanding of what exists between the stars. Or we're about to confirm that space is just full of boring rocks, and ice in 3I Atlas was an interesting but natural anomaly. That's possible too, maybe even likely. But the possibility that we're learning the galaxy is stranger, more active, more structured, more alive than the cold, empty void we imagined. That's worth exploring. The data will tell us. The universe is patient, and we're finally asking the right questions. There's a moment in human history, it happens to every civilization that develops science, when the cosmic perspective shifts, when the realization dawns that Earth is not the center, that humanity is not the purpose, that the universe existed for billions of years before us and will continue for billions after. Copernicus began it in the 16th century by displacing Earth from the center of the solar system. Galileo's telescope confirmed it. Darwin extended it. Not only is Earth not central, but humanity arose through natural processes continuous with the rest of life. The 20th century completed the demotion. Our sun is an ordinary star in the outer reaches of an ordinary galaxy, one of hundreds of billions of galaxies in the observable universe. We are not special. We are not chosen. We are a recent development on a small planet orbiting an average star in an unremarkable location. This is the Copernican principle. We don't occupy a privileged position. When we observe the universe, we're seeing it from a typical vantage point, not a unique one. The principle has been remarkably successful. Every time we've assumed we were special, we've been wrong. Every time we've assumed mediocrity, we've been right. If 3I Atlas is confirmed to be a cue ball, the Copernican principle extends. Again, dark matter has structure. It's not just an invisible gravitational influence, but a population of macroscopic objects with complexity and dynamics. This would be transformative for cosmology. Galaxy formation models assume dark matter is diffuse, a smooth halo of particles that provide gravitational scaffolding for ordinary matter to collapse and form stars. If dark matter includes macroscopic objects, those models need revision. Cue balls wouldn't replace particle dark matter entirely. There's not enough mass in objects the size of 3I Atlas to account for all dark matter, but they could be a component, a fraction of the total, adding structure and complexity we hadn't anticipated, and it would mean the galaxy is swarming. Billions of cue balls, most invisible, occasionally lighting up when they pass near stars. The space between stars isn't empty, it's dense with objects we can't see, objects that have been drifting since the universe was young. This changes our understanding of the cosmos. It makes the galaxy more dynamic, more interconnected. Stars aren't isolated islands in an empty void. They're constantly encountering these travelers, occasionally capturing them, sometimes being disrupted by them. And it poses a threat. If cue balls are common and massive, they represent an impact hazard we've never considered. Planetary defense systems are designed for asteroids, reflective objects we can track years in advance. Cue balls with thin mantles would be dark until close to the sun. By the time we detect them, there might be only weeks or months of warning. A 33 billion-ton object moving at 60 kilometers per second carries kinetic energy equivalent to tens of thousands of nuclear weapons. An impact wouldn't leave a crater, it would vaporize everything within hundreds of kilometers. It would trigger global catastrophe, fires, atmospheric dust, climate disruption, and mass extinction. The good news: space is big. Even if cue balls are common, Earth is a tiny target. The probability of a direct hit in any given century is low, but over millions of years the probability becomes significant. And if some of Earth's unexplained extinction events, the ones without obvious asteroid signatures, were caused by cue ball impacts, then this is a threat with a geological track record. If 3I Atlas is artificial, the implications are even more profound. We would know definitively that other technological civilizations exist, or at least existed, that we are not alone, that intelligence arose elsewhere and developed the capability to send probes across interstellar distances. This would be the most important discovery in human history. It would answer the Fermi paradox: they exist, they explore, but they do it quietly. The galaxy is not silent because it's empty. It's silent because communication is dangerous or unnecessary when you can send physical scouts. And it would raise immediate questions. What are they? Where are they? What do they want? The optimistic answer: they're explorers like us, driven by curiosity, gathering knowledge about the universe. 3I Atlas observed our system and moved on. No contact, no interference, just data collection. We're cataloged, noted, filed away in some vast library of surveyed star systems. If that's true, it's both humbling and comforting. Humbling because we're not first, someone else already mapped our neighborhood, possibly millions of years ago. Comforting because if their intent were hostile, we'd likely know by now. But there's a darker possibility, one that's been discussed in SETI circles and science fiction, but deserves serious consideration: the dark forest scenario. The dark forest hypothesis, popularized by Liu Cixin's novels, proposes that the galaxy is full of civilizations, but they're all hiding. Broadcasting your presence is dangerous because if another civilization detects you and decides you're a threat, either now or in the future, when you've advanced further, they might preemptively eliminate you. In this framework, survival means silence. Observe, but don't reveal, and send probes to assess new arrivals. When a planet develops technology, radionuclear weapons, spaceflight, it becomes visible. Probes come to evaluate harmless or threatening. If 3i Atlas is reconnaissance under dark forest assumptions, humanity is being assessed. Our technology, our behavior, our trajectory towards spacefaring capability, all measured and reported. And then what if we're deemed harmless, maybe nothing. If we're deemed threatening, maybe a follow-up mission comes. Something larger not designed to observe but to neutralize. This is paranoid thinking. It's the kind of scenario that makes mainstream scientists uncomfortable because it verges into speculation that can't be tested or falsified easily. But if you take the artificial hypothesis seriously, you have to consider intent. And intent ranges from benign to malevolent, with many possibilities in between. The good news: 3i Atlas is leaving. If it's a probe, its mission is ending. By late 2026, it'll be too far to observe. Whatever data it collected, it's collected. If we were going to be contacted or threatened, it likely would have happened already. Unless it left subprobes behind small satellites, quietly observing from stable orbits, transmitting data back to the departing mothership. We're not looking for those.
We're not searching systematically for small, anomalous objects in unusual orbits. If they exist, they're operating undetected. Philosophically, confirmation of artificial origin would force a reckoning with human exceptionalism. For centuries, we've been progressively humbled, not the center of the universe, not the pinnacle of creation, not unique in the cosmos. Each demotion was difficult to accept, but ultimately enriching. Understanding our actual place in the universe, however small, is more valuable than comforting illusions of centrality. If 3i Atlas is a probe, it's another step in that humbling. We're not the first intelligence. We're late arrivals to a galaxy that's already been explored. Our solar system isn't virgin territory. It's been visited before surveyed, cataloged. And yet existence doesn't lose meaning because we're not first. Science doesn't become less valuable. Art, music, love, discovery, all the things that make human life rich, remain. The universe is bigger and more complex than we thought. That's reason for wonder, not despair. There's also the question of why institutions resist these ideas, why NASA's responses have been brief and dismissive, why scientists hesitate to discuss artificial possibilities even when the data is anomalous. Part of it is legitimate caution. Extraordinary claims require extraordinary evidence. Jumping to conclusions based on preliminary data damages credibility. The history of science is full of detections that turned out to be instrumental artifacts or misinterpretations. Prudence is warranted, but part of it is fear. Fear of being wrong, fear of ridicule, fear of being associated with fringe thinking. Careers are built on reputation. A single high-profile mistake claiming to find alien technology that turns out to be a comet can end careers. This fear creates conservatism. When faced with ambiguous data, the safe choice is the conventional explanation, even if that explanation requires stretching. Better to be wrong in conventional ways than to be spectacularly wrong in unconventional ones. But conservatism has costs. It slows discovery. It prevents bold questions. And when taken too far, it becomes obstruction, refusing to look at anomalies because acknowledging them might lead somewhere uncomfortable. The balance between caution and courage is delicate. Science needs both. Too much caution, and we miss transformative discoveries. Too much courage, and we waste resources chasing phantoms. 3i Atlas is testing that balance. The data is anomalous enough to warrant serious investigation, but not conclusive enough to demand radical explanations. The next few months will determine which way the scales tip. And whatever the outcome, the philosophical exercise is valuable. What would it mean if we found evidence of other intelligences? How would it change our worldview, our priorities, our sense of purpose? These are questions humanity will eventually face, whether with 3i Atlas or some future discovery. Thinking them through now while the stakes are still theoretical prepares us for when they become real. Because if the universe has taught us anything, it's that reality is consistently stranger than we expect.
And the wise approach isn't to assume we know the answers, but to stay curious, stay open, and let the data guide us toward whatever truth is waiting. Planetary defense is a relatively new field. For most of human history, we couldn't do anything about asteroid impacts even if we knew they were coming. We were passengers on a planet hurtling through space hoping we didn't encounter anything dangerous. That changed in the late 20th century.
We developed telescopes capable of detecting near-Earth asteroids years or decades before potential impacts. We developed spacecraft capable of reaching asteroids and, in principle, deflecting them. In 2022, NASA's DART mission successfully struck the asteroid moon, Dimorphos, changing its orbit. Proof of concept: we can deflect asteroids if we detect them early enough. Current planetary defense strategy relies on early warning. Survey telescopes scan the sky, cataloging asteroids whose orbits bring them near Earth. When a potential threat is identified, we track it carefully, refine the orbit prediction, and calculate impact probability. For asteroids that pose genuine risk, we have years or decades to respond.
That's enough time to plan a deflection mission, send a spacecraft to intercept either with a kinetic impactor that changes the asteroid's velocity through collision or with a gravity tractor that uses the spacecraft's own gravitational pull to slowly tug the asteroid off course. It's elegant, it works, we've tested it, but it assumes the threats are asteroids, reflective objects we can see from far away, orbiting on predictable, trackable paths. Cue balls are different. If dark matter includes macroscopic objects like cue balls, and if they're common, they represent a category of threat that existing planetary defense systems aren't designed to handle. Cue balls don't reflect light. A cue ball with a thin mantle of ice might have an albedo surface reflectivity of only a few % similar to comets. But unlike comets that spend most of their time in the outer solar system where surveys can track them, cue balls are on hyperbolic trajectories coming from interstellar space. You don't see them until they're close to the sun and their ice mantles start sublimating. By then, if the trajectory is Earth intersecting, you have weeks or months at most. That's not enough time to mount a deflection mission. Spacecraft take years to build and launch. Even if you had a spacecraft ready to go on standby, which we don't, traveling to intercept an object moving at 60 kilometers per second relative to the sun is extraordinarily difficult. The delta V requirements, the velocity change needed, are enormous. Chemical rockets might not be capable. You'd need advanced propulsion, possibly nuclear, and even then, reaching the object matching velocities and delivering enough impact energy to deflect something with the mass of 3I Atlas would require engineering we haven't developed. So detection without adequate response time is just knowing you're doomed. The kinetic energy is the real killer. 33 billion tons at 60 kilometers is approximately 60,000 megatons of TNT, equivalent more than 1,000 times the largest nuclear weapon ever detonated. An impact would be catastrophic beyond comprehension. The object would penetrate deep into Earth's crust, possibly to the mantle depending on the angle. The energy release would vaporize rock, create a fireball visible from space, trigger earthquakes globally. Ejecta material blasted upward from the impact would rain back down across the planet, igniting fires. The atmosphere would be choked with dust. Sunlight would be blocked for months or years. Photosynthesis would shut down. Ecosystems would collapse. Mass extinction would follow. This isn't speculation. We know this scenario from studying past impacts like Chicxulub, the asteroid that ended the Cretaceous period and killed the dinosaurs. That impactor was perhaps 10 kilometers across, releasing energy around 100 million megatons. A cue ball impact would be comparable or worse depending on size and velocity. Now consider frequency. If cue balls are a significant component of dark matter, and if the flux through the solar system is 1 to 10 per year, passing within a few AU of the sun, what's the probability of Earth impact? Earth's cross-sectional area is about 1.3 x 108 square kilometers. The volume of space within, say, 1 AU of the Sun is enormous. The probability that any individual cue ball hits Earth is vanishingly small, maybe 10 to 8 per passage, but multiply that by 10 passages per year over 1,000,000 years, and you get order of magnitude estimate 1 impact every 10,000 to 100,000 years. That's uncomfortably frequent on geological timescales. Over Earth's 4.5 billion year history, there would have been tens of thousands of cue ball impacts if this estimate is right. Do we see evidence for this? Not obviously. Large impacts leave signatures, craters, ejecta layers, iridium anomalies.
The geological record preserves many impacts, but not all mass extinctions have clear impact signatures. The Permian-Triassic extinction, 252 million years ago, the worst extinction event in Earth's history, killing 96% of marine species, has no obvious impact crater. The cause is debated: massive volcanism, ocean, anoxia, methane release, possibly multiple factors. Could some extinctions be cue ball impacts? Impacts that leave minimal geological signature because the impactor is so dense and fast that it punches through the crust without leaving a traditional crater structure. This is highly speculative, but it's the kind of question we'd need to investigate if the cue ball hypothesis is confirmed. The artificial probe scenario is less threatening in most respects. A probe isn't going to impact Earth accidentally; its trajectory would be controlled. If it wanted to collide with us, it would have done so already. The concern with probes isn't collision, but intent.
If 3I Atlas is reconnaissance, and if the assessment is unfavorable, a follow-up mission might be hostile. But that's longer-term years, or decades, not immediate danger. More concerning would be sub-probes left behind. If small satellites are monitoring Earth, they're gathering data on our technology, communications, military capabilities. That information goes somewhere, presumably back to whoever sent the probes. What they do with that information is unknown. Maybe nothing. Maybe catalog us and move on. Maybe wait to see how we develop. Maybe decide we're a threat and act preemptively. We don't know. We can't know without more information. But the possibility exists, and if we take the artificial hypothesis seriously, we should consider it. What changes if we confirm cue balls or probes as real? For cue balls, we need better detection systems. Infrared all-sky surveys that can spot cold objects far from the sun. Surveys optimized for fast-moving transients. Gamma ray monitoring. If cue balls emit gamma rays as predicted, we might detect them before they're close enough to see optically, and we need response capabilities. Pre-positioned spacecraft, advanced propulsion systems, international cooperation on rapid response missions. The infrastructure doesn't exist yet. Building it would take decades and enormous resources. For probes, the response is more ambiguous. Do we try to contact them? Do we search for sub-probes and attempt communication? If we find them, do we maintain silence and avoid provoking response? These are questions for governments, for international bodies, for humanity collectively, not decisions individuals or even single nations should make alone. But first we need to know. We need to determine whether 3I Atlas is natural, exotic, or artificial. And that determination guides everything that follows. The good news, if there is any, is that existential threats from space are still low probability. Whether asteroids, cue balls, or hostile probes, Earth's cross-section is tiny. The universe is big. Most things miss us, but low probability isn't zero probability. And over long enough timescales, even unlikely events become certainties. The question isn't whether cosmic threats exist. The question is whether we're watching carefully enough to see them coming, and whether we're prepared to respond if they do. For 3I Atlas, the immediate threat is zero. It's not coming our way. But what it represents, what it might teach us about the threats that exist and how common they are, could be vital for long-term survival. We live in a shooting gallery. The stakes are high, and we're just beginning to understand what's out there in the dark. 45 days from now, or perhaps by the time you're hearing this, it will already have happened.
Telescopes will have turned. Data will have been collected. The debris cloud will either have been there or it won't, and we'll know.
Or at least we'll know more than we know now. There's a particular quality to scientific anticipation, the pause before results come in, before the experiment completes, before the observations are processed. It's not quite suspense because the universe doesn't care about dramatic timing. It's more like patience with urgency underneath, the knowledge that reality has already decided and we're just waiting to read the answer. 3I Atlas is somewhere out there right now as you listen to this, coasting through the darkness at 60 kilometers per second. It doesn't know we're talking about it. It doesn't care about our hypotheses or our debates or our telescopes preparing to observe it. It simply is moving outgassing, carrying with it whatever truth it carries. By December 19, 2025, when it makes its closest approach to Earth at 267 million kilometers, will turn every capable instrument toward it. Hubble will image it in ultraviolet and optical wavelengths.
James Webb will measure its infrared signature and spectroscopy. Ground-based telescopes from Chile to Hawaii will track it across multiple nights. ALMA will map its carbon monoxide emission, and we'll be looking for one thing above all else: the cloud. The billions of tons of gas and dust that should surround it if the acceleration we detected was caused by outgassing. The debris that must be there if this is a natural comet behaving according to physical laws we understand. If the cloud is there, massive, unmistakable spread across millions of kilometers, then 3I Atlas is extraordinary but natural. A comet with chemistry unlike any we've seen, formed in conditions we're still working to understand, but fundamentally just an icy body from another star system. Strange, yes. Unprecedented, absolutely, but explicable within the framework of known physics and planetary science. The debate won't end completely.
We'll still want to understand the nickel chemistry, the thermal regulation, the perfect in-plane acceleration, but the most fundamental test, did it eject the mass required, will have passed. And that makes the natural explanation simplest. If the cloud is not there, or if it's orders of magnitude smaller than required, then everything changes. Because at that point, the outgassing explanation fails. Conservation of momentum is non-negotiable. If the mass wasn't ejected, something else caused the acceleration. Internal propulsion. An energy source we don't understand. Physics beyond our current models. Or engineering beyond our current capabilities. Either the cue ball hypothesis with its exotic but theoretically grounded framework of supersymmetric dark matter, or the artificial hypothesis with all its profound and unsettling implications would move from the fringes to the forefront of consideration. But there's a third possibility, and it's perhaps the most likely ambiguity. We'll see a mission that's extended but not as extensive as the simplest models predict. We'll measure gas masses that are substantial but uncertain, with error bars that span the critical range between enough and not enough. We'll have data that different researchers interpret differently depending on their assumptions about gas temperature, expansion velocity, dust-to-gas ratios. In that case, the debate continues. Papers will be published arguing both sides. Conferences will host sessions where scientists present conflicting interpretations. The community will gradually converge toward consensus, or won't, and 3I Atlas will join the pantheon of cosmic mysteries that remain unresolved despite our best efforts. This happens more often than the public realizes. Science doesn't always deliver clean answers. Nature is under no obligation to make interpretation easy. Sometimes we get ambiguous signals, and we do our best with the tools and understanding we have. But even ambiguity narrows possibilities. Even uncertain data constrains the range of explanations. And as more observations accumulate through 2026, as 3I Atlas moves into the outer solar system, and we track whether its activity stays high or declines, the picture will sharpen. The International Asteroid Warning Network campaign will give us unprecedented astrometric precision. 2 months of coordinated observations from observatories worldwide, measuring position to within arc seconds, tracking any additional non-gravitational accelerations or trajectory changes. ESA's JUICE spacecraft observations from a different vantage point will provide independent confirmation of brightness and activity levels. And if someone actually points a gamma-ray telescope at 3I Atlas and integrates long enough to detect or rule out the predicted 73 megawatt signature, that's another test passed or failed. By mid-2026, we'll have a much clearer picture.
Maybe not definitive, maybe never definitive, but clearer. Enough to say with confidence whether 3I Atlas fits comfortably within natural explanations, or whether it genuinely challenges our understanding in fundamental ways, and then it'll be gone. By late 2026, beyond Jupiter, fading rapidly as it moves farther from the Sun. By 2027, too faint for all but the largest telescopes. By 2030, lost among the background stars, indistinguishable from distant galaxies and asteroids unless you know exactly where to look. Our window closes. This is a one-time opportunity. If we don't gather the data now while 3I Atlas is still observable, we'll never get another chance. It's not coming back. No return visit. No second pass through the inner solar system for follow-up observations. This is it. That's why transparency matters. That's why the high-rise images should be released. That's why every capable observatory should be observing during the December flyby. That's why this isn't just an academic question for specialists, but something that deserves broad attention and resources. Because if 3I Atlas is just a weird comet, we'll have learned valuable lessons about how diverse comet properties can be when you sample from other stellar systems. We'll have expanded our understanding of planetary chemistry and the range of conditions that produce different compositions. That's worthwhile. That's good science. It's not world-changing, but it's worth the effort. But if 3I Atlas is something else, if it's a cue ball, a macroscopic particle of dark matter with structure and dynamics, or if it's a probe, an artifact of another technological civilization, then this is world-changing. This is paradigm-shifting. This is one of those rare moments when human understanding takes a leap forward, when we learn that the universe is stranger and more complex than we thought. The risk-reward calculation is asymmetric. The cost of investigating thoroughly is modest. Some telescope time, some analysis resources, some willingness to consider unconventional hypotheses. The potential payoff, if the exotic explanations are correct, is enormous. So we watch. We wait, we observe, and we let the data speak. There's a quote often attributed to various scientists, but which captures something essential about the scientific enterprise: nature is the final arbiter. Not committees, not authority, not consensus, not popular opinion. Nature, reality, the universe as it actually is. When we argue about 3I Atlas, when we debate whether it's natural or exotic or artificial, we're not deciding its nature. We're trying to discover it. The object doesn't care what we think. It is what it is, and our job is to figure that out through careful observation and honest interpretation. That's what makes December 19th significant. Not because we've decided anything, but because nature will reveal more of its answer. The debris cloud is either there or it's not. The universe has already decided. We're just waiting to read the result. And whatever that result turns out to be, however the data resolves the process, matters as much as the conclusion. Science is not about confirming what we already believe. Science is about asking questions and following where the answers lead, even especially when they lead somewhere unexpected. 3I Atlas has given us a gift, a puzzle, an anomaly, a chance to test our understanding against observation. Whether it's a comet, a cue ball, or a probe, it's pushed us to think more carefully about what's possible, what evidence we'd need to distinguish between hypotheses, how we respond to uncertainty. That's valuable regardless of the outcome. So as you drift towards sleep tonight, consider this: somewhere out there in the darkness,
267 million kilometers away, a visitor from beyond our solar system is approaching its closest point to Earth. It's been traveling for millions or billions of years, crossing the empty spaces between stars until by chance or design its path intersected ours. In its wake trail questions about dark matter, about planetary chemistry, about whether we're alone, about what watches from the spaces between worlds. And ahead of it lies answers, or at least more data, more constraints, more reasons to look up at the night sky and wonder what else is out there that we haven't seen yet. The countdown continues. The telescopes prepare. And the universe, as always, waits patiently for us to catch up. Sweet dreams. And when you wake, we'll be one day closer to knowing.